Hello, good morning, and welcome everyone to the Clean Sheet Symposium. I'm Daniel Cooper. I'm an assistant professor in mechanical engineering at the University of Michigan, and I'm the principal investigator on this project, which is dedicated to identifying scalable strategies and building design tools for increasing the end-of-life scrap recycled content in automotive steel and aluminum sheet. And so what I'd like to do just over the next 15 minutes or so is give you some background to the project and let you know what we have in store for you today. So the energy required to produce vehicles is growing. We're using more energy intensive materials in vehicles, and we're using them to deliver better performance. We're improving safety, lightweighting, and improving fuel economy. And the result is that the energy and the greenhouse gas emissions associated with vehicle production are rising, such that when we look towards a future of sustainable transport, the issue of reducing material production emissions is going to have increasing attention on that issue. Now, one of the most effective ways of reducing material production emissions is recycling. It only takes about a third of the energy to recycle steel compared to making it from iron ore. And for aluminum, it's only a 20th of the energy to recycle aluminum compared to making it from bauxite. However, when we look at the high quality steel and aluminum sheets that are being used in vehicles, today it's very challenging to do closed loop recycling of those materials. What do I mean by closed loop recycling? I mean taking the sheets from end-of-life vehicles and recycling those back into new high-quality sheet metal that can be used again in vehicle manufacturing. And our best estimates are that for steel, there is some, but still small amounts of closed loop sheet recycling, and for aluminum, it's negligible. So what are some of the challenges? Well, the metal in vehicles at end of life is shredded and separated into different material piles. It's difficult to prevent all cross-contamination between those piles. So there may be some mixing of alloys, maybe a bit of copper wire getting into your steel pile, some ferrous rivets getting into your aluminum pile. And that cross-contamination makes it then very challenging to produce high-quality ductile sheets. And so instead, those metal piles are often exported or downcycled to aluminum castings or steel reinforcing bars, which are more tolerant often of those contaminants. If anything, it looks like the sources of contamination are going to be growing. We're going to be putting more electronics in vehicles, moving towards electric vehicles, so even more, say, copper wiring in there that can be a contaminant. And maybe even the current sinks for contaminated recycled metal may be shrinking. So I mentioned the aluminum castings there. A lot of aluminum castings are made out of recycled metal. A lot of castings are engine blocks and transmission casings. If we do move wholesale towards electric vehicles, then that sink for the recycled metal may be shrinking. On a more optimistic note, though, if we can meet the challenge of doing closed loop recycling of these metal sheets, this presents an opportunity for recyclers to be selling their material into higher value markets. And there's an opportunity for manufacturers here to close the loop on sheet metal, reduce the environmental impacts, and potentially reduce their material costs in the future too. Now, low carbon steel sheets have a long history in terms of being used in vehicle design. And then in recent years, the last decade or two, there's on an average vehicle now hundreds of pounds of advanced high strength steel too. For aluminum, again, there are examples of aluminum sheet use going right the way back. Even on the Ford Model T had a little bit of aluminum sheet used in it. But when it comes to really large amounts of aluminum sheet being put onto wheels in the US, a major turning point was Ford's decision to use to design aluminum intensive vehicles for some of their models since 2015, and maybe most famously with the Ford F-150 in 2015, the biggest selling car in the US. And so this graph on the left here just shows you for aluminum automotive body sheet, the growing wave of scrap that we can expect just from Ford in the years to come. So these are for 4 key Ford aluminum intensive vehicles. We can see that by the end of the decade, 2030, we might be expecting 50 kilotons of aluminum sheet scrap to be coming to the end of life in those vehicles, and growing to 250 kilotons by mid-century. And just to put these figures into some context here, USGS reports that in 2017, US domestic consumption of all aluminum automotive scrap, so not just sheet, we're talking castings, extrusions, everything, was just 120 kilotons. So considering the graph behind it is just the sheet metal in those Ford vehicles, this is a large opportunity going forwards. The graph on the right shows you that today, near 2020, the demand for aluminum sheet far outstrips the potential supply from the scrap metal. But that going forwards, as this aluminum wave starts to hit the shore, by 2035, potentially that the volume of scrap reaching end of life could be up to 45% of the demand, and by 2050, 80%. So if we're able to plan accordingly, there's a big potential to have very high end of life recycled content of aluminum sheet in the years and decades ahead. And that really brings us to this project. So this is a 2-year, $2 million project. This is 50% of the money is coming from the Remade Manufacturing USA Institute. So thank you very much to them for the support. And then the other 50% is coming from cost share from the 7 project team members. And these team members come from across industry, academia, national labs, and trade associations. We didn't start this project long ago. We started in May 2022, so just coming to the end of the first quarter. And we're certainly hoping that the conversations we have today can influence our research thinking going forwards. So what's our philosophy on how to approach this challenge? Well, first is to really try to understand the dynamics of scrap supply versus sheet demand. We saw a couple of slides ago that, for example, with the case of aluminum, demand far outstrips the demand for new sheet far outstrips the potential supply of aluminum sheet scrap at the moment. So irrespective of how well you recycle that metal, it could still only have a small overall recycled content at the moment. And so we're really trying to dig into understanding at the alloy level for both steel and aluminum, this scrap supply versus sheet demand, both today and in the years and decades going forwards. And then I mentioned the issue of cross-contamination. And this leads to this chemistry mismatch between the composition required for manufacturing and the composition that we actually have in our high recycled content metal. And what we're doing is trying to recognize that the potential to alleviate that concern really depends on the interplay between people at all stages of the vehicle life cycle, both sheet manufacturers, vehicle designers, and the recyclers themselves. So for example, in vehicle design, we'll be looking at if it's possible to select different materials which perhaps don't cause as much contamination at end of life. Can we fasten these materials together in different ways, which maybe make them either easier to separate, or perhaps so that the fastener itself doesn't become a source of contamination? Ultimately, what you do in vehicle design, though, how successful you are in terms of that then translating to increased recycled contents, will depend on the recycling system that it gets fed through. And in the recycling system, is there potential there to use maybe different disassembly systems before the vehicles go through shredders, or deploy new emerging separation technologies that are better at separating either alloy families or even specific alloys? Ultimately, the difficulty of separation for the recyclers will depend on how the vehicle has been designed, and how much separation is necessary will depend on the sheet manufacturer. What composition does the sheet manufacturer need? How much maybe cross-contamination can they live with? Which depends on the processes that they use. Can they use new chemistries, recycling-friendly alloys, or new processes to be able to still get high-quality products from contaminated metal? And ultimately, that will depend on the specifications that they are receiving from the vehicle designers. What are their customers wanting from them? And so what we'll be doing in this project is trying to understand the design options and investment options at each part of this life cycle, and understanding what can individual players do and how much of an effect that will have, and also what happens if we do a more global optimization approach and the whole life cycle supply chain is able to take coordinated action. And so that philosophy is driving our 5 project tasks. So I'll just go over them at a very high level. Our first task is to be able to evaluate the vehicle design space. So can we abstract, obviously a very complex vehicle design, into a recycling pertinent model, where we can essentially understand what are the key metals and where are they in the vehicle, which subassemblies, how are they being joined together, what coatings do they have, where are they in relation to potential sources of contamination. So that's task 1. And then in task 2, we need to be able to feed those sort of models of the vehicle through recycling system models. So we're modeling the performance of traditional recycling systems and emerging recycling systems. So using new technologies such as, for example, LIBS here, which has just started to be installed on a few recycling lines. And LIBS has the potential to be able to identify and separate by individual alloy. In task 3, we'll be looking at ICME, so integrated computational materials engineering, for high end-of-life recycled content for aluminum sheets. So really trying to understand how, if you do have high recycled contents, high residuals in there, how that affects the microstructure as you go through casting, rolling, and ultimately the properties of the sheet metal that you produce at the end of it. And in task 4, we're going to be looking at optimization. So I mentioned we want to know both what different stages of this life cycle could do in isolation. Maybe if nobody else changes their practices, what can you achieve? Can you achieve anything if nobody else changes their practice? We'll be looking at that. And then also what you can do in terms of a global optimization if there's coordinated action. And then last, but certainly not least, in task 5, we'll be working with Argonne National Lab to be able to update the GREET model. So the GREET model is from Argonne National Lab, and this is the preeminent vehicle life cycle analysis tool that's used in academia and in industry in North America. So this is just giving you some background to how we ended up inviting you all to today's session. What's the schedule for today? So you can see that we in the morning we have 3 sessions with speakers in each session, and the 3 sessions are broken up according to those 3 blocks of the vehicle life cycle. So in session 1, we have vehicle design and manufacturing. In session 2, we'll be looking at the actual manufacturing of the sheet metal, so sheet design and manufacturing. And then in session 3, we'll be looking at the recycling systems and technologies. And we have 3 great speakers for each of those sessions. We'll then have time to recharge the batteries at lunch for an hour. And then in the afternoon, we really want to hear even more from the audience, from you guys. And so we have a couple of breakout room sessions planned. The first one really looking at the opportunities and barriers within those individual industries, within vehicle design, within recycling, within sheet metal manufacturing. And then the second breakout room will be mixing folk up even more and really trying to see what the opportunities and barriers are for cross life cycle optimization. What coordinated action across these different types of companies could be taken to really move the needle in terms of recycled content. So just a few suggestions for today. Please attend as many of the sessions as possible. You are all incredibly busy folk, and we understand that it might not be possible for you to be here all the time. But if you could attend as many as possible, I think that'll be great and be a more enriching experience for everyone. If you have any technical difficulties, we'll be using Zoom throughout, breakout rooms. Some of you might be more familiar with other types of platforms like Microsoft Teams. If you do have any issues, please contact Mohammed. I think Mohammed has been in touch with all of you in the lead up to this today's session. And just emphasizing again, we really do very highly value the participation in the breakout sessions, and that's a real opportunity for us to hear more from you all in terms of your thoughts. just to say what the just to emphasize the focus of the project. So we are focusing on end-of-life post-consumer recycling of automotive sheet metal. So there may be lessons to learn from, say, recycling of manufacturing sheet metal scrap, or even recycling of other materials. If so, great, and we want to know that. But the focus is going to be on the end-of-life recycling of the sheet metal. Just to say that this project is not focused on steel versus aluminum versus steel versus aluminum versus plastics. That's not what this project is about. Both of these materials are going to have a strong role to play in transport going forwards. We really expect that today's discussions will inform research directions. How ultimately will all of you who are giving time today see that? Well, as I said, this is a 2-year project, and in about 18 months' time, we will organize another symposium, which will actually be a review of the draft project report that we will be producing for this. So a draft report, preliminary title there, High Value Recycling of Aluminum and Steel Automotive Sheet. And we will distribute that draft to people before the review session. And we certainly hope that many of you would be interested in participating in that review and giving us constructive feedback. And I just want to say thank you to all our speakers. I know even short talks, 15-minute talks, it actually takes a long time to be able to put them together and prepare for them. So thank you very much to all our speakers. When it comes to this morning's session, so each speaker will have about 15 minutes to present, and then we'll have another 5 minutes of Q&A. If you have questions during the talks, please type your question into the chat, and at the end of the presentation, we can relay those questions to the speaker. Also, if you have a spontaneous thought at the end of each talk, feel free to just use the raise hand feature in Zoom, and we'll get to you if time permits, and you can unmute and just ask your question yourself. Great. So without further ado, I'd like to hand over, hopefully, to Constantin. Are you in a position to share screen? And we can get going with the first talk in session 1 on vehicle design and manufacturing.
Okay. Give me 1 second.
Sure.
Oops. Okay, let's try one more.
And I believe we do have a copy of your slides if necessary. Oh, looks like things are happening.
So can you see my screen? Is the right one, or?
Yes, we can. Well, I'm assuming it's the right one. We can see material application and manufacturing for steel-intensive design vehicles.
No, I'm saying it's
a picture of the Mackie, a blue Mackie.
All right. So
you're in presentation mode.
Oh, okay. I mean,
oh yeah, you're in presentation mode. Just quickly before you start, Constantin, Mohammed's just reminded me, if you can rename yourself with including the name of your organization, that would be great. So you can just actually click on your name, and there's a rename function comes up. So that would be great if you could add your organization name. Okay, sorry, Constantin, back over to you.
Well, thank you, and good morning, everyone. My name is Constantin Chiriac. I'm a technical specialist metallurgist for research. And today I'm going to talk about material application and manufacturing for a steel-intensive design vehicle. And this is my choice was to talk about Mackie. So it's a quick overview of my presentation. I'm gonna talk about the automotive sheet steel grades. And then we'll move over the material application for for Maki, and I have a couple of slides talking about the manufacturing and technologies used for structural development of Maki, and at the end, a summary of what I was presenting here. So before going into introduction of automotive sheet steels, I want to just briefly say something about the design evolution of the BEV. So at Ford, so the first BEV vehicle at Ford, was the original BEV concept was pretty much targeting an economy type of BEV model with a very bold design. So it took strength and strong senior leadership to decide on taking up on icon nameplate like Mustang, and the launch product end up being a muscle car versus economy type of BEV. So all this the decision going from a simple bold design to a muscle car had implications or in manufacturing and material application. So that going into the material, the sheet steel automotive grades, I think the easiest way to introduce the automotive steel grades is to talk about the strength ductility diagram, or what the steel industry calls the banana diagram. So this tensile strength versus total elongation diagram lists all the existing trying to get my point. Lists all the existing automotive steels and relates with all the material application for different systems, subsystems, components in a vehicle. So the conventional steels that are colored here in green are mainly used for application that requires high quality surface, like class A applications, doors, hoods, panels, or applications that require high formability and moderate strength, like door innards, body sides, and so on. So these conventional grades here named as interstitial free high strength is the next step up in strength from IF grades. The mild steel, the BH, the bake hardening grades, the carbon manganese grades, and HSLA grades that the bubble of HSLA, or the high strength low alloy grades, the strength goes all the way up to or overlaps with the advanced high strength steel. So the advanced high strength steels started with the development long time ago. It did start with the development of the dual phase grades, followed by the martensitic steels and the press hardening steel. So later on, let's say the last 10, the grades like the steel industry worked on more formable grades with higher strength and more formable, and the trip steels came up, and followed by the ferrite bainite grades for to increase the strength of the chassis and frames, and then complex phase was the latest in the last 5 to 10 years. The latest developments in the automotive sheet steel grades are the Gen 3 grades. So these grades were designed for high strength and enhanced formability, which allows to produce structural parts using conventional cold stamping technology. So these grades, the third generation of advanced high strength steel, named here triple assisted bayonet ferrite, the TBF, the quenching and partitioning grades, the high ductility grades, which are the Gen 3, the European Gen 3 grades, and the carbide-free bayonet steel. So all these advanced high-strength steels are being applied for structural parts for body in white. I want to emphasize and mention that all these automotive steel grades that we see here on the strength ductility diagram are part of the, can be found on the Ford material specification. So Ford adopted all this conventional and advanced high strength grades. Moving to material application on Maki, we'll start by showing this exploded image of the Maki, showing the body panels, the door inners, the hood, and all that. So all the closures. So you can see that the body sides are made out of mild steel and make up to 35% of the closures. Some advanced high strength steels used for the door inners are made out up to 31%. Some mixed material with 6000 aluminum series used for the fenders and for the inner and aluminum 5000 series are used for the lift gate. There's a different application, again, mixed materials, steel, aluminum, and fiber reinforcement, plastic, and thermoplastic. Moving to material application for body in white, you can see that mild steel, it's still a part of the material application for body in white, and these are the inner body sides. And HSLA, high strength steels, up to 25% are used for the floor pan. And advanced high strength steel, it's used for the front structure for I would say energy absorption parts, and this make up to 14%. The safety cage is primarily made of forged steel, what we call the boron steel, and it's up to 30% hot stamping, hot stamp parts. The front end structure, it's made from 6000 extruded aluminum, and there are some ultra high strength steels that are used for the rocker, which includes the strongest steel that can be there. It's in our market, the 1700 Martin Citic 1700. So with that, just want to go over the manufacturing and the structural development. So the design and the development of so the development of the structural and parts and the body in white was dictated pretty much the safety regulations. Yeah. So talking about the frontal structure, so the transition from an ICE to a BEV powertrain results in a about 36% increase in vehicle test mass and the energy input into the structure. So when compare the front structure of an ICE with a BEV, the allowable crash space of the frontal structure requires a reduction of about 10%. So these design boundary conditions lead to a 53% increase in the loads that are needed to be managed by the front rails. So for that, that was addressed by an increase of, by of course applying an advanced high strength steel for the front rails, but using a higher thickness for the materials, and which also improves the robustness of the upper load pad. In addition to provide the load pad to increase the load pad to the upper structure, the shotgun that also are made from advanced high strength steel was extended to the front crash cans. The bumper, which is the, as I mentioned, extruded aluminum 6000 series, it was extended in the Y direction to engage the barrier, and a bolt was added to the reinforcement to enhance the load capacity of the hinge pillar and prevent the separation in a crash event. As we all know that the skateboard concept vehicle for the BEV allows for introduction of a flat floor. Nevertheless, in case of the Mach-E, the design boundary conditions and the safety required to increase the support to the dash cross members and under severe loading conditions, and a part which is common for the ICE vehicles was added. So this is a hot stem part tunnel reinforcement that was added to meet the safety requirements. The side impact, so the energy from a pole or barrier during the side impact must be, in case of BEV, must be absorbed before the intrusion into the battery case. So therefore, the side impact, it's using press hardening steel and hot stamping technologies for the cross members and for the side seals. And also it's using a roll form martensitic 1500 and 1700 for the rocker. So the rocker design was a 3 pieces roll form extended to the edge of the hinge pillar section to engage in for an early engagement during a crash event. This 3 pieces roll form design allows for the B pillar for the lower bottom B pillar to pass through. And this split geometry between the rocker and the B pillar was designed to balance and collapse together to maximize the energy absorption during side impact. Continue with the side impact structure. The B pillar was designed with the combination of an insert technology using a structural polymer with tailor rolled blank instead of the traditional patchwork blank for hot stamping. So which this design boundary condition was adopted in to be able to save some mass out of this B pillar. The hot stamp B pillar has a soft zone at the bottom of the the B pillar, and this in-die Taylor tempering die quenching technology was adopted for to balance the response between the B pillar and the stiff rocker section during the high loads. The manufacturing and structural development for the A pillar and the roof rail. So the roof rail impact structure is unique for the 3D roll design, roll form design. And it's using a martensitic 1700 steel tube through the A pillar and roof rail structure. The rear impact structure, it's using a hot stamp Taylor tempering in die quenching solution for the rear rail, which creates a full material strength next to the area next to the battery, and this is designed for intrusion resistance to protect the battery tray in a crash event. The solve zone, the rear end of the rail, it was designed for energy absorption. So this solve zone also includes a transition zone that is not only for energy absorption, but also for a reduction in intrusion during a rear crash event. So trying to sum up, so the Mach-E, it's a steel intensive design vehicle where the material applications were using all the automotive sheet steel grades from mild steel all the way to ultra high strength steel, the 1700. From manufacturing point of view, all the conventional and advanced stamping technologies were engaged. Also on unique 3D roll forming for ultra high strength steels of 1700 martensity grades. And the safety cage, as I mentioned, made out of forged steel, using conventional and advanced hot stamping technologies for Taylor tempered properties of the structural parts. And just to mention that for joining, because it's more of a steel intensive design vehicle, conventional joining technologies were used, like laser spot welding, laser welding, and for the front end, some for the hood was using some mechanical joining technologies. And with this, I want to thank you for your attention.
Thank you, Constantin. And we have time for just one question. There's one in the chat from Yongshin Xu of Michigan, University of Michigan. It looks like in the Mach-E, most aluminum parts are in the front of the vehicle, fender, bumper, etc. Does it mean that we can get a quite pure stream of aluminum scrap versus steel scrap if we separate the front of the vehicle from other parts?
Yes, definitely. If the business case it's there when for the recycling and end of life, definitely the front end can be separated from the rest of the car. And I assume that for the BEV, for the electric vehicles, the government, the regulations will allow, and probably the business case will be there to make recycling of these cars more efficient by allowing separating of the batteries, the fluids, the front end, things that are can be they have a higher value of recycling.
Thank you. Thanks again, Constantin Chiriac of Ford Motor Company. That's great. And then let's move on to our final speaker of this session, Laurent Chappuis. Are you able to share screen, Laurent?
Yes, I'm about to do that. Here we go. So, good morning. So I'm Laurent Chappuis. I work as a consultant for a light metal consultant, and I mostly focus on light metal, which means aluminum. And I've been asked to talk about the manufacturing aspects since I spent more than 30 years in that role, and 30 of which at Ford. So my overview of my short little talk this morning is going to be an introduction. We're going to talk about the challenge, and then the manufacturing and the selection on how we select. And ABS here is not anti-lock brake system, but auto body sheet. And then we're going to talk about some other consideration and then offer some conclusions. So let me grab my laser pointer so that I have it. There we go. And we can go on. So if we look at aluminum body sheet applications, basically we can think of two categories. And I'm a manufacturing guy, specifically a stamper. But I've looked at the problems basically from the beginning. And if you think about bolt-ons, that's anything that is attached to the body. These have short development cycles. They can be taken in, taken out for refresh and so on. And these are things like the hoods, the trunk lids, lift gate, tailgates, the doors, fenders. And then, of course, there are nowadays some isolated aluminum parts inside a sheet metal, steel sheet metal body. And then you have what Dan was just talking about, which is the aluminum sheet intensive body structures, right? And if we look at this, for the bolt-on, basically everybody is involved in aluminum bolt-ons nowadays. And many models have either an aluminum hood or aluminum doors, aluminum fenders. And it's about, believe it or not, it's about 60% of the aluminum body sheet volume in the US, right? So it's a very large chunk of what is on the road today. Regarding the aluminum body sheet intensive vehicles, Ford is the only manufacturer in the US. Worldwide, there's very few people who make aluminum intensive vehicle. Tesla makes some in the US, like the Model S and Model X, but these are not sheet-centric. They use a lot of extrusions and castings, right? But sheet-centric body structures, there's just Range Rovers in the Jaguar Land Rover in the UK, there's Ford in the US, and there's NIO in China. If we think about the challenges that this project is facing, I'll look at them. Dan Cooper explained it very nicely. I'm going to just simplify them at my level as a manufacturing person. And basically what we look at is that the first challenge is to develop a market for alloys with high recycled content. And that means compelling alloys. Then we need some incentive for the manufacturers to use these materials, right? And then you have to have incentives for the post-consumer recycling enterprise in general, which is very distributed and very large, to deliver a body sheet compatible product, right? And so if we look at the details of those challenges, what is a compelling alloy is one that has the required mechanical properties, that offers the required formability, and then that fits the cost equation, right? The incentives is basically, the first one is predictability and stability, right? And for this prompt scrap is of course of prime importance here, and for that is the stamping scrap and things that comes out, even though we focused on the end of life scrap. And then I walk into and explain why that is. And then we need compelling cost drivers for compatibility on the prompt scrap, because that will in turn help the post-consumer business. And then for the post-consumer recycling enterprise, we basically need cost-effective sorting solutions. We need a predictable market for the product that they're going to generate. And that might mean a new ISRI category or something, because right now the high value is not intrinsically recognized. A high value materials stream that would be compatible with auto body sheet does not really exist in the definition. So the question that we have here, and what's something that we have been facing, and that's one of the reasons for the project, is maybe we're facing a chicken and egg quandary, right? And so the first one is that the first problem is demand. And the demand for high recycled content alloys cannot exist if I don't have the feedstock to feed it with. And then if you think about the feedstock, well, the long lives, right? Vehicles today live a long, long time. And vehicles like the F-150, we're talking a couple of decades before the majority of them start to enter the recycling stream. So this delays the aluminum rich products into the recycling stream. And if you think about it, if you don't have demand and you have little stocks, it's difficult to envision spending money to set up a required post-consumer recycling enterprise. So going back now to something that we have that is kind of the focus here, which is what is manufacturing's influence on material selection? Well, I think the two last presentation answered that very cleanly. Body engineering, the people who design the body, right, are responsible for what material is being used. Manufacturing basically receives their marching orders and does the best that we can to deliver what we're being asked. And so if you think about aluminum alloys, because that's where my specialty lies, unlike mild steel body sheet, right, we don't have this magical things that magical carpet of mild steels in which we used to, and people still think a lot about it, in which we have these different grades from cold rolled steel grade 1 to 4, the mild steels, where we have improvement in formability as the grade number goes up. But basically, from a body engineering point of view, the mechanical properties stay the same. We don't have that in aluminum. In effect, it's even worse. In aluminum, the highest formability alloys are also the cheaper alloys, right? 5182 is cheaper. It's not the heat-treated material. It's cheaper than a skin material. And then to make things even more interesting, 5000 body sheet is incompatible with skin grades that are made out of low copper 6000 series. So as the case of the Marquis hood demonstrate, if we leave engineers to themselves, right, they create scrap incompatible design. The stamping engineers made an effort. They had a double non-attached stamping process, right, for the hood inner and outer, meaning that they're made in the same time, in the same press with two different dies, but in the same press. So if you don't want to mess up the scrap streams, you use scrap compatible alloys. But the palm dimpler is probably made outside, and it's a 5000 series. And guess what? You now have a non-uni-alloy hood. And if you were to scrap it together, you have a 5000, 6000 series mess. Some manufacturers, though, we talked about the fact that Ford, we decided to use 5182 for the door inners. Well, some other manufacturers said, well, we don't want to spend the money to invest in sorting different aluminum scrap streams. And we don't want to really pay for running those systems. So we're going to swallow the bullet. And because there is not that much difference in formability, yes, 5000 are better than 6, but in the grand scheme of things, we're not talking, extra deep draw material versus plain cold roll. We're talking, level, very subtle difference in the formability, even though we like to talk about better formability in 5000. But you can still make door inners out of 6000. You simply take a little bit more feasibility work to deliver it, but you can. And you get, of course, advantages. You might get higher strength on the door inner, so there are trade-offs. And some people have accepted those trade-offs and make actually door inners out of 6000 series. I'm thinking about Tesla and Audi, people like that. And also, another thing is that manufacturing's role can come through sourcing, right? So the program may decide to source parts to a certain factory because, of course, shipping is king and deliver just in time and everything. So collocating or near collocating stamping source is very important, and that might force you to source a particular set of aluminum parts to a certificate plant that might not be set up to deliver more than one aluminum scrap streams, and therefore you might actually gently nudge the program towards using a product that is compatible with what exists in the plant at that time. And that is especially true if you are lower volume, where on top of it, variable cost is not as important. So if we think about the responsibilities and your requirement between manufacturing and material selection, what happens? So manufacturing starts to get involved when we define sourcing, facilities, requirement, and updates if there are any. And that means that in order to be able to fulfill those responsibilities, we need to know the type of material, the alloys family, we need to know the lubricant strategy, we need the timing, we need the volumes, right? These are all the information that we need at that stage. We also, of course, support and advise the product development effort, right, towards to deliver a feasible part, which means a part that we can make. And for that means that we need specifications, we need material card for the stamping CAE to do their work, and we need, of course, again, to know the lubricants, because that defines the friction coefficient that we use in the formability analysis. Another aspect that people tend to forget is that manufacturing is often tasked with delivering prototype parts for the run of prototype parts, because we deliver those from the early tryout from the hard tool. That means that we need to have metal available for that particular stream of work, and that includes shipping to and from shops that might be far, far away and overseas. We, of course, are responsible for producing the tooling on time and on budget, right? That means that we need material available for the basic tryout, for the home line tryout, and then including the shipments to the shop and the plants and support all of that. That's a lot of more metal than you want, but mostly it is in very small quantities. So we need to manage all of that. And then finally, the final responsibility of manufacturing is that, of course, we have to make the part. And we have to do it at the required quality levels, at the required rate, and the required cost. And that means, again, even before production starts, which is the obvious when we need material, but we need materials available for all the pre-production quality loops that take place before the start of production. So if we look at timing, what does it all mean for that? It means that for material, we need material somewhere between the 48-36 months before the start of production for the step-by sourcing. Specifications and things and material cards need to be available 30 to 24 months before the start of production. And for the shipping, for all the prototype and the basic tryout, we're talking 24 to 18 months before start of production. And after that, we get closer and closer to production. If we think about timing, since we're talking about timing, the other consideration that you need to think about, and Daehn Freiberg alluded to in his presentation, is that as a manufacturer, I don't readily switch body sheet material on a production part. Actually, it's a no-no, right? On the production, from a manufacturing production point of view, you normally keep the same material for the production run. You don't even normally switch suppliers. Right, you normally keep the same source, the same material for the time of the production. So if you want to introduce a new alloy, because of the complication of introducing a new alloy and all of the other things that are involved into that, a new alloy normally is included as part of a new vehicle program, which is what Daehn explained earlier. I'm simply emphasizing it here. And what we need to emphasize is that qualifying a new alloy, any new alloy for production, involves production prove-out runs, and it involves all kinds of things, not just laboratory stuff. We need to do some production prove-out runs to define the production capabilities at the mill, and then verify how the material works in response within the various manufacturing steps. And it also means that if I want to have a new material, I need to have material cards for both the product and the stamping CAE to be available at least 36 months before any starts of production. And if you remember, if you have worked with us car manufacturers, you normally you know that we do not like to have single source available for any given material, so to avoid that situation. Which, if I turn the ship around and I look at it, the problem now from the supplier point of view, is that basically an alloy, from their point of view, an alloy has to be production ready from their facility between 48 or 60 months ahead of the start of production. And the chances of adoption of this alloy will grow if the new alloy conforms to an industry standard, right? If you have just one customer, the customer may decide, it's interesting, but I don't want it. But if you fulfill an industry standard, you immediately expand your available market. So going now to the problem that really interests us, which is manufacturing and recycling. Manufacturing is even less connected to post-consumer recycling than to the material selection in the first place, right? In the US, manufacturers like Ford are not really compelled to be involved in the end of service, end of life problem. We do this because we have personal interest or we have corporate interest or whatever, but it's not mandated like it is in other places. To date, post-manufacturing scrap is the only recycled content going into aluminum body sheet, right? There is no post-consumer scrap going into aluminum body sheet. So what can we learn from the effort that has made post-manufacturing scrap as a recycling feeding stream to the aluminum body sheet? So for this, we're going to start talking about chemical composition consideration. And I'm not a metallurgist, I'm a mechanical engineer and a manufacturing interest, right? But I've worked and developed all of the aluminum efforts at Ford from a manufacturing point of view since 1986 onward, right? So I've been exposed to a lot of aluminum questions and problems, and we have discussed it with all my colleagues. So the current aluminum alloy, if you think about them, were developed as standalone products. They were not developed as with recycling in mind. As a manufacturer, it's easy to understand that aluminum mills are manufacturing operations, right? And as their product happens to be coils of metal. But it means that they have quality operating systems that cover the cast house to the rolling mill and the heat treat facilities, right? They have all of those operating quality systems that they have that controls and guide their operations. And since the customers have tight mechanical specifications that they want out of the material, it means that they have tight operating limits. We have composition and range that everybody loves to talk about, right? They control basically 5 major elements: iron, magnesium, manganese, silicon, and copper. And if we look at the aluminum body sheets used in production today, Daehn simply showed that we basically have 5 groups. We have low and high magnesium, low and high copper, right? Between the 5,000 would be the magnesium-based alloy, and the 6,000 were based in silicon, but they have relatively common silicon levels for body sheets, but they have more or less copper. So if we look, and those of you who have seen my previous presentation, you know I love to show this. This is graphs that show the composition limit according to the Aluminum Association definition for 6,000 and 5,000 sheet. So on the left graph, you have the manganese and the magnesium, right? And you have all the 6,000 alloys that are basically used in production today. And on the right, you have copper as a function of silicon, right? Defined again for the same color coding for the same alloys, right? And those are the 6,000 used today. These are where the 5,000 land. And you can see immediately that these are not the same. The 5,000 are basically much higher magnesium content than 6,000, but they're also much lower silicon content, right? Because 6,000 are silicon-based alloy and 5,000 are magnesium-based alloys. And so you have immediately that you see that the 6,000 have lower range on the magnesium side, and they have the higher range on the silicon side. So if you are thinking about anything that you're going to refeed stock into auto body sheet stream, you need to at least segregate 5,000 from 6,000, right? That's what you need to do. If you look at the 5,000 themselves, you have here basically your low mag and your high mag, right? And you can always put low mag into high mag, but putting high mag into low mag means that you have to dilute it. Same thing on the copper side. You can see the 6111, which is your high copper, versus your low coppers, right? And that means that same story there. So if you consider that, if you consider again as a manufacturing person, if you think about the value of the scrap stream, it's always inversely proportional to the amount of work involved in delivering it. What it means that the more stuff you have to do, the less value your product can have, right? So in order to sell it as an acceptable point of view, it means you'll be buying it at a lower point of view. If you have to do very little or nothing, you can afford to buy it close to the delivery price, which means that you can offer a higher price. The trick then, and the kicker, is that actual composition ranges are much tighter than the Aluminum Association definition or the manufacturer specs, right? The manufacturer specs like Ford spec or General Motors spec or all the VDA spec are all designed to allow to encompass the chemical composition of multiple body sheet suppliers under the same specification. So they make room for each individual variations of where they position themselves. But remember what I said about a manufacturer when I'm manufacturing sheet, you manufacture it at tight specifications. So for example, this is all of the actual manufacturing specification of where the low copper body sheet end up. If you were to talk about individual composition ranges, they would be even tighter. So if you're trying to sell metal, a scrap stream to a particular aluminum sheet supplier, and you're hoping that your scrap stream can be used directly, you'll have to be very much tighter than what, at least as good as that, and maybe even tighter. Iron is another problem. It readily alloys with aluminum. Iron levels are kept lower than the Aluminum Association definition because you want to protect formability. And the aluminum scrap stream is the result of mixed metal processing in most stamping plants, and the same that it will be for post-consumer environments, right? You'll have steel mixed up with the aluminum, whether we like it or not. If you even in the aluminum hood that you see in the Ford F-150 or the Mach-E, ignore the 5,000, 6,000 issues, you have steel parts in there. You have the rivets, but you have the latch, you have the hinge reinforcements, so you have some steel parts in there. Over spec condition, when you receive a scrap stream that is over spec, means that you have to sweeten it with primary or some source of pure scrap. And if you think about primary on top of it, iron is present in primary ingot. P1020, which is the standard feed for our auto body sheet, the 20 in there stands for 0.2% iron to begin with. So if we look at the challenges of iron segregation for scrap tolling, this is now talking with the scrap from the stamping plant, and we have much faster turnaround that you would have at the end of life. If I have 1% iron in my scrap stream, and my scrap stream represents 40% of the feeds of the metal that is going in to make into the flow of metal into the stamping plant, right? Because the stamping plant, the parts use 60% of it, 40% loops back and makes this infinite loop that loops back and forth, right? You can see and these are stochastic model, right, by the way. So there's a stochastic ranges around 15.15 of the iron content in the ingot, and there's around 1% or 0.5% in the scrap stream. And you see that in order to achieve my 0.3 and meet the specification for that particular body sheet, if it was 0.3%, you would have to have less than 0.2% iron content in your scrap stream, which is less than 2 kilos per ton of scrap.
Laurent, this is a great presentation, but just to keep on schedule, could you just wrap it up?
We're arriving to the end. We're almost
fantastic.
So the steel, it means that you have strict steel segregation out of this process. If your material utilization, meaning that the percentage of scrap going into your flow of metal to make the sheet, percentage of scrap increases, then you have to be even tighter than the 0.2% that I mentioned. So the conclusion is that the first one is to remember that in the US, the majority of the aluminum body sheet is on bolt-on body parts. The material selection process, manufacturing's influence lies in the consideration of recycling the stamping scrap. And then that without consideration of recycling of the stamping scrap, product engineers are usually left to themselves and tend to design scrap incompatible design. Industry-wide spec would facilitate the development and acceptance of high recycled content aluminum alloys. And that at this time, only stamping scrap is recycled into body sheet, and that therefore the stamping scrap tolling loops and learned lessons can serve as an interesting reference to understand the requirement of introducing post-consumer scrap into aluminum body sheet. And you can think of the post-stamping, the manufacturing scrap, and priming the post-consumer recycling part. That's my presentation. I thank you, and I'm open for questions.
Hi, Laurent. That's great. Are there any questions? I think that was a really enlightening talk. Just to keep us roughly on schedule, I suggest that we, as no questions have come in, we take a 5-minute break and meet back at 10:05, and then we can start session 2, which will be we have a series of good talks from Novelis, Nucor, and University of Michigan, looking at the actual sheet metal manufacturing process itself. So let's take 5 minutes and meet back at 10:05. Thanks again for the talk, Laurent. Great work.
Mm-hmm.
Hi, Rajeev. Are you online?
Yes, Dan, I'm online.
Okay,
Can you
great.
hear me?
Yeah, I can hear you crystal clear. If you want to start sharing screen, we can just get ready for
Okay, let's
your
see.
presentation.
I have the screen. Do you see my screen?
Yep.
All right.
Yeah, that's the correct mode, and that's 10:05 too. So fantastic. We can start session 2, which will be on the actual sheet metal manufacturing itself. And it's my pleasure to introduce Rajeev Kamat from Novelis for our first talk. Over to you.
Thank you, Dan. Thank you for inviting me. And as the previous speakers have already talked about automotive sheet, I'm going to spend a little bit of time on the alloy and production of aluminum sheet. I'm based in Novelis Global Research and Technology Center in Kennesaw, Georgia. I'm a senior principal scientist and technical fellow, and I work primarily in the Global Automotive Technology Group. So in terms of the talk, here is the outline. Just want to re-emphasize the recycling aspect of aluminum. I will share the Novelis's decarbonization roadmap. Then we get into some of the alloys, wrought alloys, especially 5000, 6000 that you already heard from previous speakers, but get into a little bit of detail. And then end with some recycling opportunities and challenges. So in terms of, why does recycling of aluminum make sense? I think this is known, but I want to just emphasize the fact that, first of all, aluminum, as we say, infinitely recyclable material. We can keep doing the recycling forever, literally, by tweaking the chemistry as needed, but it doesn't lose its value. So about 70%, 75% of all the aluminum produced in history is still in use. And then the key benefit of recycled content is really comes down to energy and the emissions. So typically primary synthesis of aluminum from ores takes a lot of energy and emits obviously CO2. And numbers can be seen. This is the Aluminum Association report that talks about the life cycle assessment. And as you can see, the primary energy demand and the using recycled aluminum difference is very large, almost 15, 16 times. And the amount of CO2 emitted is much less than what you would get out of the primary. So the reason the primary takes so much energy is a couple of things. One is we actually have to take bauxite ore and refine it into aluminum oxide. Bauxite generally has 30 to 50% of aluminum oxide, but also has iron oxide, silicon oxide. So if you wonder about where the iron and silicon comes from, that's basically the ore itself. And depending on the quality of the ore, you have more or less amounts of those elements. So the whole refining process is a very high energy intensive process, given the type of ore we are talking about that takes very high temperatures to refine. And then, of course, the primary side, you have the alumina turning into aluminum by electrolysis. That involves energy as well, but also it has a lot of emissions in terms of CO2 because we use carbon anode, graphite cathode. So there is the reaction that leads to CO2 emission. So that's where the recycling makes a lot of sense. And last point, again, we heard already about closed loop and end of life recycling. We really believe both of those are going to be helping the aluminum to greater sustainability. And I'll spend a little bit more time on that, talking about it. So this is the Novelis's decarbonization roadmap. as you can see, we are talking about baseline of 2016, and trying to see if I can get my cursor. So you can see that, as I said, baseline 2016, and by 2026, we want to reduce by 30% the carbon emission and really become carbon neutral by 2050. And here are some of the key aspects in terms of scope 1 and 2. Scope 1 and 2 is generally referred to as the ones that is the direct emissions from the reporting company. Scope 2 typically because of the electricity, water usage that the company employs. And scope 3 generally indirect. It could be downstream activities, long-term investments, things like that. But you can see the one in green is where we are focusing a lot of our effort now. And of course, the one that is in blue is where we think we have to go to maximize the closed loop and closed loop recycling system. And of course, there is the whole decarbonization of the primary metal that is happening to some extent. So let's talk about the alloy systems. Again, this is something already has been mentioned by previous speakers, but I want to give you a little bit on the wrought alloys. As you can see, there are sort of 8 buckets, if you would, depending on the alloy composition. The 1000 so-called are relatively pure alloys, with iron silicon being the predominant element. As you move through left to right, you see aluminum copper, aluminum manganese, and then 4000 is aluminum silicon. The most common for us to talk about is the 5000 and the 6000, as already mentioned. 5 is aluminum mag and 6 is aluminum mag silicon with copper. And of course, there is a 7000 that's used mainly for aerospace, but we are also exploring the 7000 for high strength applications. And those that do not belong to any of this end up in the so-called 8000, the other category. So wrought alloys are typically deformed by hot and cold working, such as rolling, extruding, drawing, and typically it is sheet plate, extrusion wire, cable. And then the strain hardened, which is basically mostly non-heat treatable alloys. We use the work hardening and the anneal or the heat treatment combination to get to certain etch temper, so-called. And the heat treatable alloys, such as this 6000, 7000, we end up doing the heat treatments to get to a T temper. So this just gives you a breakdown of the alloys. So as you can see, this is from the Aluminum Association alloy designation system that's been around since 1954. And roughly there is, I believe, 500 plus alloys registered today. Again, you can tell by this distribution, it's really dominated by 6, 7, and 2000, 5, 6, and 2 and 7000 alloys. So there was talk about P1020. I just want to share this information. Basically, yes, P1020 refers to 0.1 silicon max, 0.2 iron max as the 2 elements that are how it's defined as a P1020. But if you look at the other grades, we do have higher purity grades as well as lower purity as shown here. So obviously the cost of this high purity grades is going to be even much higher than the P1020, and depending on the need, the application people are using it. And of course, where the primary is made is also important in terms of type of energy used, whether it's hydro, whether it's coal-fired. So that is also a factor in primary production. So I'm going to spend a couple of minutes on the production flow path or process flow path. So we start with casting. These are typically large ingots, 20, 30, 40,000 pounds. Depending on the alloy type, there are certain casting recipes we use. Once it's cast, it goes through a scalping step to remove the oxide layer on the top. And then it's homogenized. Hot rolling is typically done in 2 stages, so-called breakdown or roughing mill. And then it's a tandem mill as shown here with 3-stand tandem in this case. So hot rolling happens to be the really most important part in terms of microstructure and texture and surface control. So we spend a lot of time making sure that the process window is well defined. So we have a consistent product coil to coil and within the coil in terms of properties. So as I said, hot rolling is a very key part. One comment on casting, as I think Laurent mentioned, we do have very narrow chemistry limits, operating limits as we call them, to make sure that we get the right product at the end of the process. So having that narrow range is very important to meet the product requirements. So that gives us a little bit of challenge. If it is outside those limits, we may have to scrap the ingot or divert it to a product that doesn't need that level of chemistry that's in the that ingot. So hot rolling is typically followed by cold rolling, and cold rolling obviously means typically under 100 C, and it is generally to reduce it to the final gauge. Depending on the type of alloy and the mill horsepower, it can be 2 pass, it can be 3 pass, or it could be just 1 pass. So it depends on what it is that we are trying to get to in terms of final gauge. Following the cold rolling, the material goes through the solution heat treat step, and that is where we dissolve the soluble particles, and that's how you get your heat treat response in the paint baking side of the customer plants. So delivery and customer processing and paint baking is where the customer handles it. Just quick images here. This is a melting furnace where you can see hopefully the bright brightness due to the temperature. And then this is a so-called pusher furnace where we homogenize this ingot that is coming out, and just a cold rolling coil showing the mill is in the back. You probably cannot see it well. So in terms of actual mechanical properties and other things, we look at this as solving a puzzle depending on the customer requirements. So it could be surface quality is a part of the puzzle, depending on the type of requirement. As Dan Freiberg said, outer quality, it's extremely important to meet the Class A requirement. Obviously, cost is important for customers, and then this, depending on the type of application, strength, corrosion resistant, formability, etc. So you can see there are a number of requirements that end up, having this puzzle pieces put together. There's going to be some trade-offs depending on the customer needs. So we select the composition and processing to solve this puzzle. One thing missing here, as you can see, hopefully, is recycling and sustainability, which is extremely important and becoming even more important based on all the discussion we are having. So that is becoming a key part of the puzzle for us to solve as we are talking. Some of our customers are emphasizing recycling and sustainability even more so than other things, including cost. So it's definitely a departure from past ways of doing things. So just a quick look at the 5000 series alloys. Again, the dominant two alloys are 5754 and 5182. There are specific things that each of these elements do. So for example, manganese and chromium are so-called dispersoid forming elements that control the texture, grain size, and to some extent strength. But the dominant element that's in the 5000 is really magnesium, mag, that actually has impact on the strength, and actually it has small impact on the density because it's lighter than aluminum. Copper can play some role, especially if you want to explore heat treatable heat treating effect. So some suppliers have played with copper as a means to get a little bit of kick in the paint bake, for example. Titanium is grain refiner, and then silicon and iron in this case are really impurity elements that come from depending on the type of primary used, as well as recycling scrap that we use in the making of these alloys. So again, this is probably already mentioned, but just to make it clear, so 5754 is.
And Rajeev, just a heads up, if you could start wrapping it up, that would be great.
Okay.
Thank you.
So 5754 is generally for structural applications, and 5182, as we heard, hood inner as well as door inner type. The benefit of 5000 is there is no natural aging, but it also doesn't have any kind of paint bake response, or it does not really meet the Class A surface quality. So this is something I'm going to skip here because it's, I think most people know in terms of 6000, it's heat treatable with mag and silicon being the dominant alloy elements. So this is also was discussed. So we have a bunch of alloys that are low copper and high copper, sort of the broad categories. One of the things I do want to emphasize is the role of iron and manganese. As you can see, they do affect bendability. Having them higher amounts of iron is definitely hurts or impedes bending and potentially formability in general. So we have to pay attention to this. And one of the things we do think that would make a lot of sense is to really have uni-alloy concept. So in terms of 6000 for structural as well as inners instead of 5000 would go long ways in terms of scrap compatibility as well as end of life and even joining and potentially down gauge by replacing 5000 alloys. So just the last slide. I think we are okay with this left graphic that talks about where the source of scrap is. But I think the key things I want to emphasize is, first of all, we need to upcycle. As we heard, a lot of the more than 90% of the post-consumer end of life ends up in the casting alloys. We have to develop high scrap containing alloys. That's an ongoing challenge. And in fact, recyclability should be an integral part of alloy and process design. Closed loop, obviously very important. And again, uni-alloy or fewer alloys is something we have to think about. We really have to be aware of the scrap quality and consistency. For example, recently, we ended up with a twitch analysis that had 0.7 iron, which is very high, and we would need a lot of primary to dilute it. But that contamination comes from, as we heard previously, rivets as well as parts. I think I mentioned this already. We have to, recycle-friendly design, and advanced sorting is something very important given the projections for the end-of-life scrap that's coming. And last but not the least is really having a life cycle analysis versus manufacturing. So not just looking at the manufacturing, but product use cycle as well. And I'm going to end here. I'm not going to go through this, but we are partnering with Sortera. this was announced a couple of weeks ago, where we are using, going to start taking the new production scrap and end of life switch scrap processed by Sortera and supplying into our plants. So this is where I want to stop. If there are any questions, please let me know.
Thank you. I think maybe we have time for one quick one, which was referring to the primary aluminum ingot grade. So I think you were mentioning, say, P1020, and then there were some that were a bit worse and some which were a bit better. So the question is that for the ones which had even lower iron content, is this just driven by essentially the quality of the ore, or even for metal that ends up being used in sheet metal, is there extra refining steps beyond the normal electrolysis that this is going through to get that iron down?
So I think we have to go through further electrolysis, and it also depends on the quality of the ore. It's a combination of the things.
Okay. Is P1020 the workhorse when it comes to primary material that will end up in sheet metal, or could it be any of these?
It could be any of them, but as the lower levels of iron silicon goes, the price goes up. So P1020 is by default the workhorse.
Thank you. Thanks again, Rajeev, for nice presentation. So that's great. So we've had a talk there on from Novelis, aluminum sheet manufacturer, and then up next we have a talk from a Nucor, so a steel sheet manufacturer, Dane Kanelos from Nucor. Are you online and able to share screen, Dean?
Yes. Let's see. Do you see my screen? Hold on.
Yeah, we can see it. You're not in sort of presentation mode, but we can see your presentation.
Figure out where my presentation. Okay, got it. Okay, let me go there. Okay, there we go.
Yeah, you're good.
Hi, I'm Dane Kanelos with Nucor, and I'll be giving a presentation on the steel manufacturing as it relates to the scrap supply. First off, in the steelmaking process, there are two basic types of steel manufacturing. There is what's referred to as the integrated mill process, and there's also the mini mill process. In the integrated mill process, you have coal, which goes through a coke oven that's fed into the blast furnace, and you also have limestone, which is converted into burnt lime in a kiln, and then fed into the blast furnace, as well as iron ore. Iron ore typically, after it's mined, it's enriched, and then it gets made, typically, at least in the United States and in most areas, it's made into iron ore pellets prior to being charged into the blast furnace. So you have those three ingredients going into the blast furnace. And over in Asia, you'll find a lot more of another process, which is producing what's referred to as sinter, which is a little bit of limestone and iron ore combined with coal. And it produces an intermediate product that ends up getting fed into the blast furnace. But most of that is I'll call it a less efficient process, and you don't see that in the United States, and so we don't deal with that here in this country at this time. But anyhow, so the blast furnace, these elements are fed into the blast furnace where a natural gas is injected into it, and ends up being heated up, and then out of the bottom comes what we refer to as blast furnace iron. Can also call it pig iron to an extent, although it's not a pig until it's actually cast into a pig. And the blast furnace iron, or hot metal as it's referred to, gets transferred over to the basic oxygen furnace vessel, the BOF vessel, where it is where an oxygen lamp will blow the hot metal with oxygen at supersonic speeds, and that the purpose of that is to oxidize the carbon and the silicon in the iron, which is an exothermic reaction. It also refines it and purifies it, and then that will make the steel, and which gets poured out, and that becomes the steel that's used for casting. In the mini mill process, we use scrap which is taken from various locations. I'll go through that in detail, as well as direct reduced iron. Some might use hot briquetted iron, but it's the same thing. It's basically the iron ore pellets that we were talking about that the blast furnaces use, and it goes through a kiln where the oxygen is driven off and therefore made into a basically elemental iron that can be used as a scrap substitute. This is a more recent development. We use DRI, and with the limitations on how much scrap is available, it becomes very valuable for us to use more DRI in the future. So that is fed into the electric arc furnace, and we have we dump it into the furnace, these elements, and then we strike an arc using electricity and heat it up. Typically, electric arc furnaces also use oxygen injections into the furnace, so will work out similar to a BF vessel to an extent, but that's to speed up the process. And then it's tapped out. From here, and I don't show the process, it will go over on both of these. So we'll go over to a little metallurgy furnace where the alloys are added and the steel is refined, and the inclusions are removed, and the final product, the final chemistry is produced. Then it goes over to what is called the casting, the continuous caster. There are two types of continuous casters that are typically being used. There are variations of these, but I'm going to go through these main types as being the types that are used for steel making. There is the conventional slab casting, which is used by the integrated mills. So you'll find the conventional integrated mills that use the BOF blast furnace production process will cast these cast slabs at roughly 200 to 300 millimeters thick, 8 to 10 inches, and you get a 1 to 2 meters per minute casting rate with that. Goes through it goes their torch cut goes through a reheat furnace, or it could be taken offline and banked. The slabs can be banked, which is typically done because the integrated mills will take those, will make one particular grade of steel in large quantities, and cast the ones that are necessary, and the ones that are not needed immediately will be banked for later. That way they don't have to do, how do I say it, production changeovers where you have to have different alloys made back to back, and that way it improves the casting sequence of the manufacturing process. But anyhow, so it goes through the reheat furnace where it is soaked into normalizing temperatures. It goes through a roughing stands, these roughing mills at high temperatures. It may go back and forth through a coil box if necessary to retain the temperature, but essentially goes back and forth through the roughing mills until it gets down to a lighter gauge. And then it goes through a set of finishing mills, whereas in tandem they get rolled down to final gauge. Goes through past a run-out table where it is quenched and cooled as appropriately to attain the final properties, and then the coil goes to what's called a down coiler, where the coils are coiled up and then finally cool. Typically a coil might be 20 to 40 metric tons. It could be a little larger than that, but typically not less than that. For a thin slab caster, which is typically how the mini mills or the EAF mills produce it, but not exclusively, but this is a variation of it. Really, we go with a much thinner slab, usually a 50 to 60 millimeter thick slab, and our casting speeds are several times faster than an integrated mill, a conventional slab casting. But it goes into what's referred to as a tunnel furnace. And in other words, you don't use a reheat furnace where it's soaking the temperature. It's already at temperature, and we do not bank slabs because they're thin. You can't bank them. So they go straight through and then directly over to the finishing stands for final gauge. Some mini mills do have a roughing mill put in there as well, but you don't see that as often. But we do have several that do have roughing stands as well. Then it goes into a run-out table where it's finally cooled, just like above in the conventional slab casting, and then it is you end up with a coil, basically the same type of coil, the same size as the conventional slag casting process. Okay, so let's see. That's basically the hot mill process. Cold mill is just basically taking the steel and cold rolling it to final gauge after it goes, and then through a bell anneal process for final, at final gauge if it's going to be a cold roll product, and then it could go through a galvanizing line. I didn't go through all those details because it's really not necessary as far from a scrap standpoint, but just wanted to let you know what from a scrap standpoint, an integrated mill will typically use roughly 25 to 30% scrap in the BOF vessel. It is added to the scrap adds the iron content to the blast or the BOF because of the excess temperature created by the BOF vessel. So all that oxygen you're injecting, which oxidizes the carbon and silicon, creates a lot of temperature, and they can add the scrap to dilute it essentially with the scrap. EAF mills, they range from 50% scrap to 100% scrap, depending on their use of the DRI and pig iron. Pig iron being blast furnace iron that's formed into pigs and added to the furnace. These are scrap substitutes. The bar mills typically do not use DRI. They typically use just exclusively scrap. And sheet and plate mills will use DRI if they have barge access. The reason they do that is because DRI is kind of a finicky thing. You can't just store it outside. It has to be stored in silos and kept dry. So because it has to be handled in bulk, typically DRI is only handled and used by the large sheet mills that have barge access. There are two essentially two categories of scrap we could refer to. One is obsolete scrap, which is recycled post-consumer scrap. Typically, obsolete scrap will have a typical copper content. I'm going to talk about copper because it is an important thing to control in scrap for its final use. We'll have a typical content of approximately 0.28% copper. So you have shredded scrap, which you see on the left, and you have plate and structural scrap, which is composed of demolished buildings and other structures. And these are the two common types. When we produce scrap, we segregate it into these piles so that they're separate, and that there's a good purpose for that. And one of them is because we want to be able to segregate the residual content of these different types of scrap as well. Shredded tends to have higher copper content than plate and structural. And then there's prime scrap. Prime scrap is also prompt industrial scrap. It's also considered a pre-consumer scrap. It doesn't ever made it into a final product, and it is recycled prior to getting going into a final product. Scrap is typically it's from stamping operations, it's the flashings and other things for that. And it has a much lower copper content because because it's not contaminated with copper from wires and armatures and things like that. We'll have a copper content of approximately 0.08%. Busheling is another form of that. So you have the shredded and you have busheling, and all busheling is also referred to as number one shredded scrap, but it's essentially a low density, or it's a high density form, and the low density form would be the bundles on the left side for using to charge into the furnace. Scrap substitutes include pig iron, which you see on the left, and small ingots produced from the blast furnace side, as well as DRI, which is shown on the right. Scrap substitutes have essentially zero residuals, carbon, tin, carbon, nickel, molybdenum, tin. This is eliminated because it is not contaminated with any of these elements because they're not added anywhere upstream. Primary elements in steel, just to give you an idea. Carbon, manganese, phosphorus, sulfur, silicon are the primary elements. Aluminum is added in boron and microalloys including titanium, vanadium, and niobium. These are oxidizable elements, meaning that when you charge them in the furnace and you heat them up, they are oxidizable. They can be removed from the steel and are not trap elements. Trap elements are considered the elements that cannot be removed from the steel during the steel making operation, and they stay with the steel, after scrap is added. It retains those alloys, and that's copper, tin, nickel, molybdenum, and chrome are the primary. There are others there, but these are the ones that we primarily deal with. Chrome is semi-tramp, but it's still considered tramp for our purposes. Copper is the element that we monitor the most because it has the most effect from a quality standpoint. The rest of them we consider just going along for the ride for the types of scraps that we use. Alloys in automotive steel, typical mild and HSLA steels, we use carbon, manganese, aluminum, silicon, boron, and microalloys. So these are all oxidizable, and so they're not really an issue as far as recyclability. Martensitic and press hardenable steels will use the same, as well as might use some chromium. Again, not a big deal for most grades that are being produced. When you get to the third gen steels and the dual phase steels, you might use potentially some chromium, nickel, and molybdenum. These are more of the tramp elements that are added into the mix. That although they will add those residual elements to the final chemistry, they're typically not a problem when it comes to recyclability, and can be used in most steels. Scrap segregation is important. We do that before the steel is charged into our furnace. So busheling or prompt industrial scrap is inherently low in residuals. Like I said, it's about 0.08 copper, and is not mixed with obsolete scrap. It's separated, and we charge it separate. Shredded or number 2 dealer bundles has a known amount of residual elements, and we know that, and we factor that into the steel making process. Plate and structural has a predictable amount of residuals, higher than busheling, but lower than shredded, and we have a pretty good handle on it. So when we charge a furnace with certain proportions of the amount of scrap, we have a pretty good idea of where the residual elements are going to be based on the scrap charge. So, and steel mills monitor these residuals primarily by regulating the copper levels, because copper is the residual element that is most concern to us. Why do we want to limit the residuals? Well, high residuals will raise the tensile strength, make it difficult to meet the low strength properties of DBS and EDDS grades. So they're most ductile grades. It'll be used for body outers. We have a tough time getting the mechanical properties. You got to keep the residuals relatively low for that. And also elevated copper levels on heavy gauge items will cause what's referred to as hot short, also known as liquid and metal embrittlement on the surface. So we can only use so much copper, and by measuring the copper, everything else goes for the ride. We typically are pretty good with the rest of the residuals. And how do we limit it? There's a few different ways. One of is dismantling and removing the copper wiring before shredding or baling. This is done at the scrap yards and dismantlers. Also, hand sorting copper from shredded scrap. It's very labor intensive, yet it is done quite often because the cost of adding that copper, having low copper scrap is important. I mean, it's valuable, and that is actually the primary way in which low copper scrap is produced right now. Ballistic separators are used, and that's basically taking call it a jumping conveyor that goes over a roller that uses a magnetic roller that throws the scrap at different distances based on the amount of copper that's in there, or basically how magnetic it is. And that's starting to, you see more ballistic separators that are used to produce low copper scrap. And also there's we use scrap segregation based on residual content. So if there's a low residual content, we'll separate it in different piles so that we don't mix it in with the higher copper scrap. That's basically it. If you have any questions, let me know.
Thank you, Daehn. Great talk. Any questions? Just one from me is in one of your first slides, you showed in the mini mill scrap and DRI going in the United States. Is Is it always DRI as the scrap substitute, or it can still be pig iron too? Is both going on in the US?
Pig iron is used as I didn't throw that in because there's not nearly as much pig iron as there is DRI. DRI can be used as much as 50%. Pig iron can be used. We use a lot less of it now. I mean, I'm going to say we use maybe, I don't know, 5% pig iron in a charge on a typical basis for the sheet mills. Some of the bar mills don't use any pig iron. And I can tell you that in 2020, because of the relative shortage of pig iron due to the Ukrainian conflict, we cut our pig iron consumption in half. So pig iron isn't necessary, but it does improve our processing. As far as cycle times to produce steel. So we tend to use some pig iron. So it becomes part of that equation as well. Okay. Yes.
I guess one thing, just looking at the numbers, I think you said it would contain at least, the EAF would contain at least 50% scrap. The shredded scrap still has quite a bit of copper in. So does that mean that to get above 50% and still be able to produce sheet, you're mixing that shred with a lot of, say, manufacturing scrap too, to be able to control that copper level? We
will mix the amount of shredded scrap, which is basically shredded scrap is number 2, or it's basically appliances and automobiles that have been shredded up, and that'll get charged into the furnace. We'll use a certain ratio of that based on the copper scrap mix that's required to be able to obtain the copper levels that are necessary for the grades of steel we're producing. So if they happen to be low copper requirements, typically a low copper is we refer to it as less than 0.1 cent copper. Then that would be, we call it 10 copper scrap mix. Those are low residuals, low copper, and so we use a much higher scrap charge with more busheling and less shredded scrap to be able to make that. That is the ratio of busheling to number 2 scrap or shredded scrap will vary, but it'll also be higher busheling or post-consumer or pre-consumer scrap content for charges that don't have DRI, because DRI doesn't have any residuals and will take advantage of that. Whereas the mills that use DRI will use a much higher post-consumer scrap mix, more shredded. And so some of our mills that use DRI up to 50% DRI, they might use a 50-50 charge between pre-consumer and post-consumer, whereas the mills that the sheet mills that don't use DRI will use roughly closer to an 80% shredded scrap. Busheling and 20%. Now the integrated mills, they typically use about 80% busheling. So that can vary based on the grades of steel that they're producing. And I don't know the details as to why and how they do it that way, because I'm not there, but they can vary as well.
Okay, thank you. And actually, just one quick one that's come through the chat. Is there any EPA regulation for collecting or cleaning those oxidized elements?
Cleaning the oxidized elements all come out in the baghouse. And I also didn't include zinc in there because zinc ends up is oxidized. It's not an element in the steel. It's actually the coatings that get oxidized. And that gets picked up by the baghouse at the baghouse. But they're in such low, and also in the slag, for example. But those really, you can't really reclaim anything from the slag. The slag is reclaimed and reused, in various applications. It's 100% recycled, but for different applications, like as a substitute for gravel, for pavement, things like that. But the baghouse, the baghouse dust is all sent and reclaimed, where they pull the zinc out of there and it gets reclaimed. But most of those, like microalloys and other elements that they get pulled out, in such small quantities, there's just no way of reclaiming them.
Thank you, Dean. Great talk. Up next, so finishing us off for session 2, we have Professor John Allison from the University of Michigan, a world-leading expert in ICME, Integrated Computational Materials Engineering, to tell us a little bit about what it is and how it applies to this project. Over to you, John.
Okay, great. Can you hear me and see my screen fine?
Yeah.
Okay, great. Thanks, Dan. And thanks for the invitation to talk here. So what Dan asked me to do is give a brief overview of what integrated computational materials engineering, ICME, is, and by reference to work that we did at Ford. I spent a number of years working with Laurent and others that are on the phone here, Zoom here at Ford when I was there, called virtual aluminum castings. And then to talk a bit about one of the tasks that we have in the Clean Sheet program, applying that to ICME to improving the recyclability of aluminum sheet. So ICME defined is the integration of materials information captured in computational tools with engineering product performance analysis and manufacturing process simulation. And I like to emphasize that this materials information comes in many forms, and often it's empirical or experimental information that we try to capture in these computational tools. So we have a number of great manufacturing process simulation tools that help us understand the thermal histories and strain histories during manufacturing. We have great engineering product performance analysis tools that help us understand how to do crash or fatigue or what have you. Often these product performance analyses are driven by static average properties, and the goal for ICME is to replace these constitutive models with manufacturing history sensitive constitutive models. And so then we link this process simulation, go through quantitative processing structure property relationships, and that ends up in the driving the product performance analysis. So when we have that, we can do more robust and rapid process and product optimization, or we can drive it backwards and innovate new alloys or new manufacturing processes. So the Ford virtual aluminum casting experience was an experience that I led for a number of years. And it revolved around powertrain castings. So where right now all this great recycled aluminum tends to go, and a little bit of iron here and there. At any rate, so we have these models for doing casting and heat treatment. And then the basic idea, and these might be MagmaSoft or Procast, is use that to predict the effect of casting and heat treatment on local microstructures and properties. Then that feeds the durability or crash prediction. Over here in the case of powertrain, it was largely fatigue properties. And using this manufacturing history sensitive information, we could optimize more rapidly our powertrain components. So this required understanding of how both casting and heat treatment affected the key microstructures that we were concerned about for castings, and these four properties. So we had to understand how all of these pieces went together in the processing structure property. And that meant that we had to really understand key microstructural processes and how those affected how manufacturing history affected those different scales differently, and how those impacted properties. Here's an example of when we did that on yield strength. So we would start off with a CAD geometry of a V6 block, do the casting analysis where we'd filling and thermal analysis. So then the new piece was then using that detailed thermal analysis to predict local microstructures, in this case, aluminum copper phase, theta phase that comes out during casting, but then you can solution treat it and heat treat it. That was all done virtually. And then finally predict yield strength from that information. And so as an example, we have here might be a V6 block where we see the gradation of properties around that block. a particular bolt boss target strength was 220, but we predicted it was 210 MPa. Now, prior to having virtual aluminum casting, we would have, of course, had to make tooling. We would have had to cast the part, section that, and pull the tensile, and we would have discovered that we were below what the product engineer wanted. And so then we'd be back to changing the heat treatment, changing the casting process, tweaking the alloy or whatnot. Now with something like virtual aluminum casting, we did this prediction long before we even thought about ordering tooling. And so we could, in this case, tweak the heat treatment and get the desired properties so we could get it stronger and do that treatment more optimally, do a faster heat treatment. So this paid off at Ford. So we reduced product and process development time by 15 to 25%, improved our launch quality and reduced scrap, eliminated failures during product development, and overall reduced cost by over $120 million. And that's a number that we had at around 2010 when I left Ford. I suspect it's doubled since then. But also interesting, we took all this expertise that we had in cast aluminum metallurgy and provided it in a consistent way to our entire Ford powertrain operations around the globe. So just to then wrap up the ICME part, ICME, and there are a lot of other exemplars that were studied by a National Academy study back in the 2008 time frame, provides a means to link science and engineering, manufacturing, the materials and design, experiments. I always like to emphasize that are an important part of ICME, theory and simulation, and information across disciplines. So relative to the clean sheet program, ICME for recycled aluminum sheet is this is, as far as I know, the first time we've attempted to do this. The objectives in the clean sheet program are to develop this ICME capability for predicting the influence of composition residuals on manufacturing yields, and to use that to enable the design of alloys and processes that are tolerant to fluctuations and increases in residual content. So here's the flow chart that Rajeev provided us and provided me. Thank you, Rajeev. So we need to do this at several points along the line: casting, homogenization, hot rolling, cold rolling, and solution treatment. And ultimately, you'd like to have formability and the effect of paint bake. Within the 2 years that we have and the funding we have, what we're focusing on are solidification, so microsegregation and second phase formation during DC casting, homogenization, whether it occurs here or back here, and solution treatment and phase dissolution, and finally hot rolling, which is largely the topic of texture formation. And this also is in 5,000 and 6,000 series alloys. The tools we'll be using are a lot of microscopy, SEM type microscopy, microprobe analysis, EDSB, backscatter, and EBSD, as well as Gleeble for thermomechanical simulation of the rolling operations. On the analytical side, we have thermocalc, Dictra, and if we needed it, precipitate simulation, and this includes high throughput simulations that Fatih Sen from Novelis will be doing in this task. Also analytical micromodels that we've developed at University of Michigan around microsegregation and recrystallization, and finally using crystal plasticity for texture prediction and simulation. So since we've just started, we don't have that capability yet. So I'll show you some examples from other areas that we will be applying to this program. So this is some work on solidification, microsegregation, and microstructures that I was doing with my friends at Ford, Mei Li and Yang Kuo, that my student Zhenjie Yao recently completed. And so this looks at copper microsegregation across the dendrite, you can imagine, or as a function of fraction solidification. Traditional models for this might be thermochile models. And so we see here that copper in particular, primarily because of its high large partition coefficient, actually is substantially higher in microsegregation within the alpha aluminum than we might predict by these classic models. And so we've developed these micro models, comprehensive models that take that into account, as you can see here. Similar for the homogenization and solution treatment, we've got a couple of things we need to think about there. One is dissolution of phases, and in these aluminum copper, this is in a die-cast 380 aluminum alloy, some work that Shenyang Shi and Tracy Berman in my group were working on with a lift project. And so we used a thermocalc dictra to model this phase dissolution and homogenization. And so you can see here the predicted the measured dissolution of phases, and the predicted using classic dictra modeling. And we have some tricks in our bag of tricks here for improving these simulations. And so one has to take all these models with a grain of salt until they're properly validated and verified. And similarly, the homogenization from EPMA predicted from dictra simulations and measured by EPMA. So we'll be using this in the dissolution. And finally, in the texture formation and as well recrystallization, we use the Glebel for doing sheet rolling texture evolution. So we model the rolling process with plane strain compression, our Glebel shown here. So this would be the rolling direction. And the example I used here is from a US AMP program for GM and Chrysler Materials Consortia, where we were working on a sheet, but this was magnesium sheet that's formable alloys when you get the processing correct. And so using the Glebel, we were able to optimize the manufacturing history to get the desired texture. This is a very texture important problem, and this was recently published in Journal of Metals to get this sort of soft texture, formable texture. Then within our Prism Center, we're now modeling that texture evolution. And so this shows some recent Prism's plasticity, crystal plasticity modeling of that to get the desired texture. And so that's also some recent work that we've completed. So we'll be using this basic concept now for rolling of sheet products. So just to wrap it up, ICME offers a means to link science and engineering. Importantly for this community, manufacturing, materials, and product development, and information across knowledge domains. Virtual aluminum castings is an example where we developed this comprehensive suite of CA tools that captured an enormous amount of expertise in cast aluminum products and provided that to a global engineering workforce. We hope to apply that approach here within the Remade Clean Shape project to take all the expertise that this group has to plug that into a state-of-the-art ICME capability for predicting the influence of residuals on manufacturing yields and alloy design. So with that, I will stop and take any questions. Thank you.
Thank you, John. Great talk. Any questions? There's one in the chat here. How much and what main sources of uncertainty do you typically encounter with your ICME projects?
Well, there are many and varied. So it's a lot of it has to do with uncertainty of the manufacturing variables themselves in terms of the empirical data that goes into this. So making sure that that is well understood when we're doing the empirical part of that, I would say is a principal source of uncertainty. Again, validation is very, very important. Taking data models without doing the proper calibrations is a really fraught problem. And so that can also be a source of uncertainty, is lack of validated models, I would say.
You mentioned sort of it when you were introducing the concept that often as mechanical engineers we'll use an average value and put that into Abacus for our engineering simulations. I just wondered with the sort of back and forth, or was there any back and forth when you were at Ford where maybe you found out that the yield strength was different, maybe lower in some areas than what the product engineer had desired? Were there any cases where they actually revised what they truly wanted? As in, were they able to refine what they actually wanted in different parts of the product rather than just sort of assuming a single value?
Well, so we were able to use location-dependent properties in our final analysis. So that was frequently done. I mean, that became part of the Ford CAE process now, is to use location-dependent properties to account for those location, those manufacturing history sensitive properties. So yes, they do use now those different properties rather than the average properties, at least for aluminum castings.
Okay, and was that a significant change? I'm just thinking if you're designing, just making some, you're designing a block of metal. I assume that they looked at the most critical part of that component, decided what the properties of that material must be at the most critical point, and then just assumed that the whole thing should have those properties. Was that sort of the older way of doing it?
Well, not really, because oftentimes those critical locations are difficult to get material properties from. Take a valve bridge and a cylinder head, very critical area, but it's a very tiny area. And so it's not really possible to take average properties from that. So oftentimes that was done by build it and bust it testing. And so basically using this approach, we replaced a lot of sort of average properties with large safety factors and lots of testing. So substantially reducing the testing requirements and improving the designs at the same time.
Okay, awesome. Thank you, John. Any other questions? Have I missed any in the any hands up or anything? I don't think so. So thank you again, Professor Allison. Let's have
my pleasure.
Thank you. And that wraps up session 2 on sheet metal manufacturing. Let's take a 5-minute break. Shall we meet at well, let's make it 11:15 for session 3, which will be on recycling systems. So let's meet at 11:15.
Mhm. How's it going? Good.
Hi, David. Are you online?
Yes, I am online and I am visible and unmuted. I'll take it you heard me since I did not hear you.
Just letting you know, David, we can hear you, so all good.
Great, thank you. Hopefully you can see, it tells me you can see my screen.
Yes, yeah.
That's great.
Okay.
Hello, can you hear me? Sorry, I was having a few headset issues there. Great, well, welcome to session 3 on recycling systems and technology. David, would you like to kick us off?
Sure, thank you, Daniel. Appreciate being invited to talk. I'm hoping to set the stage for the following speakers of this session. I'm going to talk about recycling of end-of-life vehicles, or ELVs, an overview of the U.S. system. So an overview, I'm going to talk a little bit about ISRI, who we are, recycling, specifications, ELV recycling, and some closing thoughts. So for those of you who do not know the Institute of Scrap Recycling Industries, we're the voice of the recycling industry. We're a Washington, D.C. based trade association that has more than 1,300 members all over the world and in North America. There are manufacturers, processors, broker traders, industrial consumers who melt down, say, metal that's produced by our recyclers, and also have equipment and service providers as part of our membership. At least for 2021, we're a $117 billion industry, recycling more than 140 million metric tons of material. You can see the table on the right. More than half of that is iron and steel. Non-ferrous is a much smaller component, dominated by aluminum, copper. You can see the table. As you may not know, paper and fiber are second at 46 million metric tons. And then there are some relatively minor amounts of other materials that our members handle. Again, our members handle ferrous and non-ferrous metals, paper, plastics, tire and rubber textiles, electronics. So I want to talk about a key ISRI concept called design for recycling. It goes back actually to 1986. You can see on the right, that's the sort of the title of an article that was in the Phoenix Quarterly of ISRI's predecessor. Design for recycling, the idea came out because consumer durables had hazardous components and non-recyclable materials, and it created problems for the recycling process. And that evolved into ISRI's design for recycling principles. And there are basically 4 of them: is to eliminate or reduce the use of hazardous substances or materials that impede the recycling process, to maximize the use of materials with recycled content. We've heard from speakers earlier today about, that's a desirable goal. On the other side is to have products that yield the maximum amount of recyclable materials at end of life, and that kind of completes the circular economy, that the product is both the demand for recycled content, is also a producer of recycled content. And lastly, and with relevance to this Remade project at the Remade Institute, it's working with manufacturers, government, and other stakeholders to achieve these goals. This is probably one of the hardest things to do. Someone asked about EPA's authority to do anything regarding the manufacturing. They really don't have authority. So it's really comes down to sort of agreements among the various stakeholders, manufacturers, recyclers, government, to work together to achieve these goals. And Remade is kind of an embodiment of that, working with stakeholders. The design for recycling is also consistent with the 12 principles of green engineering. As you might be familiar, there's the source of it at the bottom. The things I like are design for separation, conserve complexity, durability rather than immortality, and minimize material diversity. Some of the discussion about the design of vehicles kind of ran counter to, say, minimizing material diversity and conserving complexity. Vehicles are very complex products, so it inherently presents recycling challenges, and the recycling system needs to adapt to it as well. I'm not going to talk about all of these recycling definitions, and you might be wondering, why am I putting this up here? Is because if you look at the federal law that affects recycling, which is the Resource Conservation Recovery Act, it talks about recycling but doesn't define it. And there are many organizations out there that have their own definitions of recycling, and ISRI is no different, but and that's certainly an ongoing discussion right now. But I think the way to think about recycling, and I just want to point to the last sentence of the first bullet, is that it's the series of activities that include collection all the way to the resulting consumption of the material by a materials manufacturer. So the way to think about recyclers, that as we call them, is they acquire recycled material, which is defined there. They process it into recycled material, and that recycled material ends up as the input to a material manufacturer like electric arc furnace or secondary aluminum. So talk about some conditions favorable for recycling. And these may be common sense, but they're actually kind of hard to do in practice. Sufficient material value, have intrinsic value, sufficient material available for recycling. Recycling is what I would call a high volume, low margin business. And because technology tends to be very expensive, there's a big incentive to put the most material you can through it to drive down unit costs. Recyclers, and I'll get into this later, cost-effective recycling technologies, and that is somewhat related to how things are designed that get recycled. Efficient material logistics, some say that material logistics add up to about 50% of the cost associated with recycling. And then of course you have the value of the material that's getting recycled. Markets for recycled material, as mentioned in the definition of recycling, if you really don't have the material end up in a market being used for manufacturing, then you really haven't accomplished recycling. And then finally, favorable policies, laws, and regulations. Policy might be, say, designed for recycling. A regulation such as exists are things like the exemption for unprocessed scrap metal being recycled, so it can move like a commodity, and then the exclusion from solid waste of processed scrap metal and also prompt and home scrap metal. So those things help recycling, especially of metals. So let's talk about markets. Markets rely on specifications. Recycling is a commodities business driven by demand. We're not in the service business. Our members collect and process material because of the value of the material to produce commodities that are demanded in the market. Again, it doesn't matter how much you collect and process. If you don't have a market, you haven't really accomplished recycling. So ISRI for decades has maintained specifications, and they represent what manufacturers are willing to purchase if it meets the specifications quality requirements. The specifications provide a global standard for consistency and quality, reflect tolerances allowed by manufacturers, and provide a common language. And there's a saying in the industry, an old industry adage, that scrap is bought, not sold. And what that means is that recyclers typically cannot dictate what the value of their product is. The value of the product is whatever the buyer says it is. So it's not as if recyclers can upgrade the quality of recycled material and then say to somebody, we want to charge $20 a ton more for it. It doesn't work that way. It's pretty much what the buyer says the value of the material is, which makes recycling a very challenging thing at any given moment in time. So let's talk about ISRI's commodity specifications. So this is a picture of the current specifications. I expect a new one to come out shortly, which talks about our guidelines for non-ferrous, ferrous scrap, and other materials that are commonly traded in the market. These specifications represent what is, they're not aspirational goals, such as if we create the specification, we hope that people can meet it. That's not the way these specifications work. They really reflect what is going on in the market now. And I think Laurent talked about the wish for a new ISRI specification for sheet, whether it's steel sheet or aluminum sheet. And there is no specification because simply it's not widely traded yet. When it gets widely traded, ISRI certainly has the ability to create a specification that reflects what is being traded. So that's kind of it's a little bit of a chicken and egg problem, as that was mentioned. So here are some specifications related to ELV recycling. That's not all of them, but you might be familiar with them, especially the non-ferrous, Twitch, Tweak, and Zorba. I think there was discussions about the amount of iron in some of the aluminum, and Twitch has a lower tolerance for undesirable metals such as iron relative to Tweak, and then Zorba is a mixture of aluminum, copper, lead, magnesium, and stainless, and other metals in there. And on the left side, there's the ferrous, which is shredded scrap, and they pretty much differ by the density, which relates to essentially how the shredding process is accomplished. And it doesn't have specific limits on other metals that are in there like the non-ferrous specifications do. So this is a broad outline of ELV recycling. I won't tell you that every vehicle follows this process, but I think it's a good representation of the vast majority of vehicles that hit end of life. And there's an assumption in this whole thing too, is that vehicles are sold where the buyer, initial buyer, owns the whole vehicle and can do whatever he or she wants with the vehicle. Vehicle ownership, if it changes, such as you can never own a vehicle, the seller always owns it, or the OEM always owns it, this might change. But right now, with the buyer owns the vehicle, so vehicles reach end of life on average 10 to 15 years after original sale. It might have up to 10 different owners. The ELV is acquired usually in lots based on reuse and recycling value, and they're bought because the value of the reusable parts and the recyclable materials exceeds the total cost of acquisition, depollution, processing, and so forth. So ELVs, at least traditional ICEs, represent a positive net value, and they're bought on that basis. That is, the recyclers buy their inputs and sell their outputs. So on 3, reusable parts are harvested from the ELVs by dismantling for sale as used parts. And dismantling can be conducted in self-service or full-service modes. The self-service mode might be that the dismantling location allows the public to come in and take parts off themselves, more the do-it-yourself model. And the full service is that they acquire end-of-life vehicles and they remove parts based on what they understand market demand is for used parts. For instance, I recently, a few years ago, had a transmission replaced, and the service dealer found a used transmission that fit my vehicle by calling around to various different locations to find if they had exactly that transmission that fit my vehicle. So after the parts are harvested, the remainders are recycled by shredding and separation to produce specification grade ferrous and non-ferrous metal commodities. Usually the ELV remainders are densified for transport to a recycler for shredding. And sometimes the shredding operator owns the self-serve dismantling location, or the shredder operator buys from a dismantler the ELV remainder based on the net value of the recycled material in it. And I think this is relevant to some of the discussion we've had so far, is that ELV remainders are shredded with other types of metal bearing end-of-life materials and products. So ELVs are only some of the input to shredding operations. They're not the only input to them. And then finally, completing the recycling, the specification grade metal commodities are bought by consuming facilities such as EAFs and secondary aluminum as their process inputs. So let's talk about the infrastructure for ELV recycling. There's more than 300 metal shredders, and I put commodities because that's their business. There's approximately 10,000 auto dismantlers, and their business is used parts. My understanding is that most of those dismantlers are really small mom and pop operations that might have 1 to 5 people. So there's a lot of those distributed all around the country. And the map shows, at least in the case of shredders, where they're located. And generally they're located where the material is. That just stands to reason. Some states don't have any because the population density is very low. About 95% of ELVs get recycled, and 80% of the ELV material is recycled. So talking about the shredding segment of the US recycling industry, again, there's more than 300 shredders in the US. It's actually really hard to count them accurately. I've seen recent publications say it's 306, 307. It's probably about the right number right now. A majority of those shredders are owned by one shredder companies. There are some companies that own many of them, but majority are single shredder companies. The motor median or mode size is 400 horsepower, but they go as high as 10,000 horsepower. Again, this is a subset of the 300. And the throughput median, that is the rated throughput, is 12,000 tons per month. Again, that's a subset of these. It may not be entirely reflective, but the largest ones are about 5 times larger, that equate to roughly more than 300 tons per hour. So if you're going to have a shredder that can process 300 tons per hour, you need to buy material to feed it. And that can be a challenge. You'll notice the historical shredder count. It's grown kind of rapidly in the last few decades, but in recent decades, it's kind of peaked. Whether that is indicative of we've kind of hit the maximum amount of material that's available for processing, that we can't really sustain more capacity, or something else. And certainly dematerialization is probably part of that. As you reduce the mass of things, there's less stuff to recycle, which will put pressure on the recycling industry. Annually, there's about 17 million automobiles are recycled. That fluctuates with the economy. That might be a pre-COVID number, but it's roughly equivalent to sales, but that might change. Also, they processed 45 million appliances. Last year, 96% of ELVs were recycled by shredding, and 78% of end-of-life appliances. I think the simple way to understand the difference in those percentages is that you can landfill an appliance, you really can't landfill an ELV. Not all appliances end up getting recycled. So I'm going to talk about shredding operations. So really the first step is inbound material control. They accept ELVs, end-of-life household appliances, other end-of-life light gauge mixed metals. There's variation by shredder as to the specific mix. Some might have an equal amount of ELVs and other materials. Some might have more ELVs relative to other materials. Some might have less. It's an industry practice to have tools to minimize the acceptance of undesirable materials. And here, this is a sign at one of our members that shows you what's not accepted and what is accepted, but only with proper identification and other requirements. And you can see, I won't read through the whole list, but these are the things that shredder operators use to make sure that they're only accepting what they want and can recycle through the shredding process. And it doesn't present problems for the recycling process or for the quality of the materials that they produce. So the shredding itself. So on the right is a diagram of a shredder. You can see a vehicle being compressed by a double feed rollers going into the hammer mill itself. And you can see the particles inside the hammer mill moving around, and they drop through the grate and come out on a conveyor for later separation. You know, there's variations in in-feed chutes in shredder style, side load, top load. The hammer mill, it's a rotor with swinging hammers within the enclosure. There's a picture, sort of the exposed rotor with some hammers in it. I think it weighs tens of tons. And on the right are new hammers, which can weigh anywhere, you know, on the order of 500 pounds each. And those are used that get swung around and pulverize material into fist-sized pieces, which become, as we call, raw shredder aggregate, which is pre-sorting, pre-separation. So downstream separation, this picture here kind of shows you a view from the in-feed to the shredder, and then beyond the shredder, it goes to a magnet, and then it goes to non-ferrous separation. So the ferrous metal is typically separated out from the raw shredder aggregate by use of magnets and maybe further processed to meet quality specifications. It's usually conducted in line with the shredder. The thing about a magnet is it only responds to magnetism. It's not very it's not selective at all to the steel alloy that happens to be present. So it basically collects all the steel that's in everything that was ever shredded, and that composition is somewhat variable, maybe place to place, if not over time. After the steel is removed, the remaining materials goes to separation to remove non-ferrous metal, and there's a variety of separation technologies. There are trommel screens, eddy current separators, optical scanners, dense and heavy media. Different methods of sorting are used, and there are some newer ones being developed with newer technologies. And the non-ferrous metal separation may be conducted inline or offline, depending on the nature of the shredding facility and its relationships with its downstream partners. So I have some closing thoughts. The current US recycling system for ELVs is configured to produce used parts and specification grade shredded metal commodities. ELVs that are shredded have variable composition due to vehicle make and model year. Again, we recycle the past, and it's kind of a superposition of everything that was ever sold and came out of use. And the composition is also related to any prior removal of used parts. The composition of the specification grade shredded metal commodities reflects the composition of the shredded ELVs and any other metal bearing end-of-life materials and products. That kind of makes sense, input, output, but it also is somewhat subject to the specificity of the separation processes. Does the magnet get only steel and does not get other metals or other materials? And does the non-ferrous separation processes get only non-ferrous metals, or do they get other things in it too? And does some metal escape both processes and end up in material that ends up going to landfill? And then finally, recycling of sheet metal from ELVs likely requires new recycling methods or technologies and changes in vehicle design. Again, no one is going after at end of life sheet metal to shear it off, to rip it off certain parts of the vehicle. There was a discussion about whether you can sort of chop a vehicle in half and remove the aluminum rich part from the steel rich part. That really doesn't exist yet, especially since we recycle the past and vehicles weren't necessarily designed for that. So it's something that I think would be difficult to do in practice, at least in this open loop system that we have, where everything ends up going to the same place, and it's not sort of not only closed loop, but very thin closed loop. Anyway, I'll end there. I appreciate your attention. Happy to answer any questions in the remaining time.
Thank you, David. Thank you. And I think we have a question from Professor Greg Keolian. Would you like to unmute yourself, Greg, or if you prefer, you can type?
Sure.
Sure. Over to you.
Thanks, David. That was very helpful with what you presented. Just in terms of the modeling of material flow, do you have good statistics on how much of other products are processed through these shredders? Referring, for example, to the white goods, like how, just volume of white goods versus, automobiles that are shredded.
If you mean detailed data, that's something I don't have. I know that we have done surveys of our members that operate shredders to try to get at some of that information and try to come up with some kind of industry average. Again, industry average, might represent nobody because it's an average. And in some places you'll be ELV heavy, in some places you'll be appliance heavy. And I'm not saying heavy might be, instead of 80-20, it's 60-40. So I guess it depends on how detailed the model is. I mean, if you're talking about doing it at each one of the 300 shredder locations with detailed mass flows, I doubt we'll get that.
No, just that we can give, rough idea of the split, just the volume overall for the country would be helpful. And in terms of the ferrous product, is that a number 2 bundle, like in terms of the classification of the steel, and does it end up going to rebar, casting? Does it go to any of these EAF facilities?
That's a great question. So
integrated mills.
So part of that is due to the open loop nature of this. So, and maybe if we have some members that we're willing to share, and I appreciate their participation today. Our members they might even sell by broker. So they don't even know who they sell to directly because the broker makes the market. They might know of say a steel mill that needs 100,000 tons of material, and they know of a variety of suppliers from our membership that have material that they can aggregate to provide to that, let's say, steel mill. It's not usual. I'm not aware that our members always know what will be made from the products that they produce. So again, in my understanding, it's really the buyer's market. And again, the decisions by automotive manufacturers affect the decisions by the EAFs and the secondary aluminums, which affect the decisions made by the recyclers. Unfortunately, the material goes one way and kind of the information goes the other way. In terms of what requirements are.
Yeah, what's possible, like if these do end up with integrated mills that make sheet, for body in white, or they end up more, being used for rebar and things that are less, stringent in terms of composition and contaminants.
Yeah, it's a great question. So my understanding, it tends to go to rebar, but I kind of had an evolution of thinking about so-called downcycling, and I'm not sure it makes sense to take really high quality steel and put it into an application that doesn't require it. I'm not suggesting that everything should get downcycled, but I think there's probably a balance somewhere to sort of minimize effort and maximize utility. There's probably some equilibrium if it's attainable there.
Okay.
Awesome. Thank you, David, and thanks for the question, Greg. Let's move on. So next up we have.
I will stop sharing. So.
Oh, thank you, David. Emily Molsted from VALIS. Are you able to share screen?
Oh, yes, absolutely.
Great.
Sorry, I'm on the web version of Zoom today for some reason.
Okay.
Just a second. Okay. Perfect. Can you see that okay?
Perfect. Yeah, over to you.
Fantastic. All right, well, thank you for having me today. I'm excited to talk to you about the process and systems around aluminum recycling and their criticality. My apologies, it's jumped way ahead. So I thought I would just give you a little bit of a background on me. So I'm fairly familiar with a lot of the people on this call, but I want to just kind of shed some light on my background. So I'm VALIS CEO and co-founder. VALIS is a software startup dedicated to delivering the data and software solutions that are needed to enable a metal circular economy. And a large portion of my understanding and experience within the scrap industry really started when I was entrepreneurial lead through the National Science Foundation Innovation Corps program. So through that program, I had the opportunity to travel across the country and interview over 150 industry stakeholders within the metal recycling space and really gain an in-depth understanding of the ecosystem and the challenges that it's facing without being directly, at a processing plant or in a recycling facility. And then I have an engineering background and have carried out research in recycling prior to my experience with the scrap industry. I'm going to jump through, the first couple of slides. I think we're all very aware of at this point, right? Aluminum contributes significantly to human emissions at 2 to 3% of all global emissions, and 90% of that comes from primary production. And so there's a really pressing need to reduce the emissions associated with aluminum production in order to meet sustainability goals. So the International Aluminum Institute has actually set a target requiring a 77% reduction in emissions associated with aluminum production. So just a quick summary of, by the numbers, we have an 80% increase in demand by 2050. 90% of all emissions are coming from primary production. In order to meet our sustainability goals, we need a 77% reduction across the aluminum industry. And a really key piece of that is delivering on a circular economy. And so what is important about a circular economy, right? Why is recycling so essential? Today, it avoids 300 megatons of CO2 emissions. That's equivalent to if you removed more than half of US vehicles off the road for a year. And so it's a really impactful industry and really critical to the success of overall aluminum production, but there's still a long ways to go in order to be delivering on all of the needs that are required for aluminum production through recycling. And so just at a really, really far out bird's eye view, you have, as David conveniently broke down, it's really great to have David set the stage going into this, that you have your collection process, then you have your processing where it takes that collected material and gets it into a form that's ready for the remelting and refinery process. So that can then move on to reutilization in manufacturing. And it's really critical to look at the recycling process based on which material streams you're evaluating, right? So we're familiar with pre-consumer scrap, right? So it's your new and runaround scrap. It's really clean. There's minimal contaminants, and the composition is relatively known. There's internal processes in play to maintain separation and packaging of this material, so it makes it really easy for recycling. So pre-consumer scrap has high collection rates, low metal losses, and it currently meets 13 to 14% of demand. And something to note here is that it currently meets 13 to 14% of demand, and it's projected to meet that same level of demand in 2050. And so there's a lot of emphasis around actually minimizing the generation of pre-consumer scrap through minimal waste manufacturing processes. And so that material doesn't need to be recycled in the first place, it's just retained in manufacturing. Now, of course, as we're all centered in on is post-consumer recycling and the opportunities and challenges that in line with post-consumer recycling. So as you can see, there's a pretty stark difference in what post-consumer aluminum looks like. So you have a mix of raw and cast and painted pieces and organic contaminants and other metals that can get mixed in. So this is all of your material from the end of life goods. It's extremely mixed, higher contamination, and also as David mentioned, right, we're recycling the past. There's a gap between when the material was manufactured and then it's when it's being reutilized. So there's that inconsistency between the alloys that were originally used and the alloys that are needed today. So post-consumer scrap today meets 20% of all aluminum demand, and it's projected to meet upwards of 40% of demand in 2050. So really driving at, there's a lot of potential and a lot of material that's going to be generated as we increasingly use aluminum right through lightweighting initiatives, and we need to be ready to capture that as has been established and set up through this symposium. So just an overview on some of the main commodities and sort of some of the names that David again alluded to some of these. Twitch being a major one. This is your automotive aluminum, has a very high recycling rate. The content being heavy on the 6000 series side. So that's actually that content's really coming from your 5000, your 6000 from those white goods. And it's mixed in with a significant amount of cast as well. You have your taint and tabor, which is your clean mixed old sheet. It also has a high recycling rate as well and contains ranges from 1000, 3000, 5000, 6000 series alloys. And then talc is your post aluminum can scrap, so a significant portion of that sheet. And that has a much lower recycling rate at 45%. I mean, a well-known composition of 3000 to 5000 series. So if we look at what are the specific challenges and opportunities within each step of the recycling ecosystem to maximize post-consumer recycling. So if we're looking at collection, pretty straightforward. You have your cars going to your scrap yards, really high collection rates there. You have your cans going through municipal solid waste facilities or deposit collection facilities. And then you're building scrap, your demolition scrap being sold directly to scrap yards and scrap processing yards, which also has a very high recycling rate. A major challenge here being the UBCs, where collection rates here are much lower, resulting in $800 million worth of aluminum going to landfill each year. And so there's, of course, an incentive to really focus in on how you can increase UBC collection rates. There's a number of systems and companies focusing in on this space. You have the reverse vending machine from Tomra. There's some startups looking at how to really drive consumer incentives to recycle. But it's really critical to note that 100% collection is not enough to meet the recycling rates that are required for sustainability goals. Even at 100% recycling rate, 100% collection, you're at a less than 90% recycling rate. And so we need to be driving at how we can increase the sorting, because that decrease in recycling rate is related to that mismatch in composition as has been talked about. And so you have your mixed scrap, which is, as has been mentioned, typically downgraded into your cast with significant alloying content. And there's that need to separate out your wrought from your cast, and then ideally further separating into the cast into high copper cast or low copper cast, and wrought into your different series of alloys, so it can be better utilized into manufacturing. And so we've seen, there's a variety of efforts out there that have evaluated the efficacy of having really high scrap content. So 100% taint and tabor scrap used in 6111. And so while this demonstrates that the potential is there, this study used manual sorting in order to achieve the desired mix of scrap. And that's not applicable within the industry and reaching sort of the economies of scale necessary to get this old scrap into the necessary end uses. So the main focus has been for increasing processing is sensor-based sorting. So there's two main sensor-based sorters. The first being X-ray fluorescence. This focuses in on the composition, and while handheld analyzers in lab settings and some larger scale operations demonstrate that you can distinguish between alloys at a commercial scale, at full scale sorting systems, there's the quality of the sensor data isn't there in order to separate within those light metals. Right, so the signal data for your aluminum, magnesium, silicon, when you have multiple, an extensive distance between your piece and your detector, it's just not an efficient enough process yet for fully separating out those alloys at a commercial scale. And then, but it is a promising opportunity in tandem with other sensors and other data processing methods. And then there's also laser-induced breakdown spectroscopy, or LIBS, and which uses a pre-ablation laser, and then the spectroanalysis from the plasma emission. And this is also really promising for really getting between different alloys and effectively sorting, but within cast and within wrought. And so it's demonstrated that LIBS has that higher accuracy for alloy identification and separation. But the main challenge here is that because it has that pre-ablation laser, the feeding mechanism is a single line, which does not bode well for throughput requirements. So from conversations within industry, really requiring a 6 ton per hour throughput, and these are currently limited with some systems, getting up to 5 tons per hour, but it's with 5 different sensor locations, which really increases the cost of these systems. And so these are high capital investments that are required, and scrap processors need to be confident in the throughput and the capabilities of these systems before adopting them. Another critical piece too is the compounds, right? So those are, if you have a aluminum piece with a bolt, that's not always going to be detected. And so that can cause detrimental amounts of iron in the resulting melt. And so there's the opportunity, and it's already coming into play with leveraging artificial intelligence, computer vision, to enhance both the identification of those challenge pieces and the further separation of alloys more economically and at the throughputs that are required. So it's just continuing to drive at how that sortation can be enhanced, and then also driving on the adoption, continuing to validate these systems so scrap processors feel confident in making that high capital investment, and then knowing that the products they're creating will have a consumer to go to. On the melting side, right, so you have your 3 main types of furnaces dependent on scrap quality, with the primary focus for post-consumer scrap being with your rotary furnace. And the major challenge within post-consumer scrap is those organic and other inorganic contaminants that can cause detrimental effects within the melt. So studies showed that within Twitch, you can get up to 0.83% weight percent of coating material, right? So if you have white paint is really, really common, that contains titanium, and so that can cause the brittleness. And then there's also challenges too with other methods for pre-treating the scrap, where char from burn-off can cause an increase in dross content. So dross being, right, that essentially waste product of the remelting. And so really prevalent within, if you're looking at UBCs, right, they typically have paints and coatings, and with all the breweries putting on pretty art labels without having effects and adhesives, you're seeing pretty substantial dross content, and so that comes from the contaminants and oxide formation during the melt. And dross can contain 15 to 70% aluminum, so it can have really, really high aluminum content, especially with the post-consumer side of scrap. So it's resulting in 960 million pounds of aluminum lost. 25 to 50% of this can be recovered through dross recycling, which is a really important part of the aluminum recycling process and ecosystem. But even with recycling that material, we're still losing the energy from the first process, right? So energy loss of 70 trillion BTUs. So you want to drive minimizing dross production, So focusing in on how can scrap be pre-treated to minimize those melt losses. And so taking it a step further, that's how we can drive a circular economy within the process and within the technology. But a really key part too is the integration of the ecosystem. So there's critical data being generated at each point along the process that currently isn't widely transferable or shareable, or insights aren't easily generated from the data that's kind of being missed or overlooked. And so focusing in on how can that data be leveraged and be fully utilized. So moving scrap recycling towards Industry 4.0, right? Increased sensing capabilities, automation, data processing. So that way you can have more informed alloy creation based on all the data that's collected on the post-consumer scrap, increased support for material flow analysis by getting a better understanding of how that material moves through the scrap process, and ultimately reducing processing costs because you'll have ensured process optimization and centered in on that profitability piece. So maximize material recovery at a lower cost. Major takeaways, right? Emphasis on that post-consumer scrap, as we're all aware. Collection being a key part of the solution, but not the only solution, and sortation really being what's going to enable that higher recycling rate that's needed for sustainability goals. Pre-treatment to ensure that melt losses are minimized. Of course, alloy design for recycling to ensure that those end uses can take on the scrap as it becomes available, finding homes for that scrap, and then leveraging the data that's available for process optimization so you can get cost parity for these secondary alloys. Thank you. And I'll take any questions at this time.
Thank you, Emily. Very nice talk. Any questions? Feel free to raise your hand or put them in the chat. Maybe just one from me to begin with. What's the effect of coatings on the ability of LIBs to pick up on the alloy?
So it is dependent right on that coating thickness. There's the pre-ablation laser, which is a benefit in being able to detect through coating. Yeah.
Okay. And I think you mentioned the effect of maybe titanium from paint too. That can be a source of contaminant in your recycled metal. The titanium oxide that was in the it's used for paint, isn't it? A lot.
Yeah.
Okay. That's interesting. That's, I don't think, something we particularly thought about before. So thank you. There's Greg, you have a question.
Yes, thank you. The question is related to what I asked before in terms of what comes out of a non-ferrous processor. Do you know where that aluminum is going in terms of application with automobiles? My understanding is a lot of the aluminum recovered would go for aluminum castings. Is there any other applications that you know of?
It's predominantly from what I've seen in the casting side, right? So historically going into your engine blocks, and so it's beyond. There's also applications beyond automotive, and there's marine applications as well. But yes, that rock content, that twitch, being typically downgraded into those cast products.
But in terms of like earlier presentations about, you know, the differences in alloys, 5000s versus 6000s coming out of the non-ferrous processor, what kind of separation there is being achieved in terms of alloys?
So there is the capability to separate between alloy series and some growing capabilities for then alloys further within those families. It's really just still early in the adoption period of that technology and seeing that at a full commercial scale. With, as I mentioned, the major limitation being the throughput that's required in order to get that more accurate sortation between alloys.
Okay, thank you.
Thank you.
Yes, thank you very much, Emily. Moving on to last but certainly not least in our morning talks, it's my pleasure to welcome Dr. Katie Daehn from MIT. Are you able to share screen, Katie?
Yes, I hope so. Okay, and I'm gonna get a timer started too.
Sure.
So does that show up well?
Yep, perfect. Over to you.
Great. Okay, so I'm Katie. I'm a postdoc working at MIT. Today I'll be talking about copper contamination in steel recycling and hopefully trying to answer some of those questions of where the scrap goes. Iron and copper is a system I've been studying in different forms throughout the last few years. So it's a thread that moves kind of throughout my career, and hopefully it is a thread that is very clear in the presentation too. And what you're seeing here is just an abstract illustration of copper in the steel system. So to get started, we've heard in much more detail and from experts that know much more about what cars are made of than I do, but this is a very back to basics representation of what is in a vehicle. So the little car here shows the proportion of different materials by mass. So by mass, an average vehicle is 1.3 tons, and the majority of that is from steel and iron. So that's about 60 to 70%. If we consider the CO2 intensity of those materials, so that's what the big car is showing. So within a vehicle, it's actually embodying a mass much bigger than the mass of the materials. The CO2 itself weighs about 6.6 tons. So this is a very significant consideration here. It's several years of driving the car is actually embodied in the materials. So steel and iron still are significant, but you see aluminum plays a big role here too. It's a small percentage on average currently by mass, but it makes up a big proportion of CO2 emissions. And as lightweighting and electrification kick into gear even more, these considerations will only grow. So today I'll be talking about steel and iron because that's my main expertise. But aluminum is another, we actually have a project coming into gear at MIT on a process to try to sort alloys, but actually doing like a color separation step with a very efficient gas, basically using gas to color the alloys differently and then sort them. So I can talk offline about that. I don't have time to fit it in today. So as we've talked about, end-of-life scrap is extremely important and it will only grow in importance. So we've seen in steel production a huge boom in primary production driven mostly by China the last 20 years or so. And at a global level, all of that is going to return for recycling within 10 to 20 more years. And so this is a projection of steel production going forward to 2050. And if we utilize that increasing scrap, we can basically just grow the market share for recycled scrap and keep primary production about the same. So we can really utilize this growing resource. The question is whether there's any technical barriers that will prevent us from really growing this market share. And so I'll be looking into copper contamination because that does seem to be the biggest technical barrier. So this is a vehicle with the copper wiring and little electrical motors highlighted within it. So you see that it's very much entangled into the vehicle itself. It is, very much a part of the vehicle. And so trying to get that, disentangle that end of life can get messy. So you heard earlier about how a vehicle is recycled. There is that hammer shredding step followed by magnetic separation. So you would imagine that the copper and the steel could be separated magnetically, but just because of this really physical entanglement, you get some bits of copper wire still hanging into the shredded steel scrap. Sometimes you get big copper meatballs following through, and those can sometimes be hand sorted, but inevitably there can be some ending up in the steel melt. And that causes metallurgical issues. At the moment, there's no practiced way to get copper out of the steel melt. But it can cause the hot shortness on the surface. It causes the tensile strength issues that you heard about earlier. So these are the tolerances for different steel products here. So reinforcing bar is the most tolerant. It can more or less accept the amount of copper that would be in this shredded scrap from a vehicle. And then your nice drawing steels, also cold rolled coils, have very low tolerance. So, you know, a small amount of a vehicle, if any, is ending up as a new vehicle. So that's the problem kind of at the product level, at the metallurgical level, I guess. If we want to understand, is this really a problem that we need to come to grips with at a systems level? Is this a problem with how we can decarbonize steel production? We have to understand the whole steel system. So that's what's shown here. It's a Sankey diagram. So it shows from raw resources to final products, how steel moves through the global industry. And this should be familiar to Professor Cooper. It was made in the group while he was doing his PhD there. So it's a bit dated, it's from 2008, but more or less the structure of the industry has kept this shape. So what I did to try to understand the influence of copper on the system is I recolored it. So what I am showing here is end of life scrap coming in. So this is transportation scrap, is this kind of darker orange line, because that is one of the more contaminated scrap streams. It gets mixed along with some DRI and possibly pig iron into an electric arc furnace. And then that steel is cast into billets, more or less, and then that ends up in the construction industry. And so what I did was looked at the amount of copper in the system and how much is tolerated across these various intermediate products that we demand. So I wanted to see, is it a problem how much copper we're trying to send through the system versus how much we can tolerate? And the quick answer is that no, currently it doesn't seem to be a problem. In fact, we could almost double the amount of copper coming in, and if it's fed to the appropriate construction applications, it's not currently a problem. Of course, this is already a bit dated, and trends are changing. So I tried to look at a baseline scenario. If nothing were to change, if we kept our scrap preparation practices the way they are, but we have this large growing amount of scrap on a global scale, will we be able to demand it in the products? Will we be able to tolerate it in the products that we demand? So the amount of copper in scrap is shown in this dotted line. So the orange line is a base case scenario. The solid line is the amount that can be tolerated in demand. And so it shows that we're really in this kind of comfortable spot at the moment for tolerance, but it will start to constrain around 2050 is when we could see some severe limitations and, just tightening before that. And I should note that this is all at the global scale. So this is assuming that you can get the contaminated scrap to where it needs to go anywhere in the world. Of course, things get trickier if you have, regions and distances to consider. So this is work done by Professor Cooper's group that I am very appreciative of. It shows what the US steel system looks like currently. And as you can see, about 100 million tons of steel goes into the steel stocks in the US each year. And about 74 million tons of scrap arises. So the US is a nice, it's reached, as we might say, stock saturation, more or less. So the amount of scrap that's coming out is becoming somewhat equal to the amount of steel that we demand. So within the US, we could establish a nice circular steel system. The problem is more or less the copper contamination. So that is analysis also in this paper shows that copper may already be causing constraints. That might be the reason why there's this scrap exported here. It might be the reason why we have import of certain goods here. So copper contamination is a problem we will have to come to grips with if we want a circular system in the US. And vehicles is a great place to start to try to tackle that issue. So the vehicles, this is highlighting just vehicle scrap in this system and the vehicle steel that makes a new vehicle is shown in the blue there. And it is very much as a global average, an open loop. End-of-life vehicles become reinforcing bar. Cars are made nearly exclusively of iron ore plus some forming and fabrication scrap. There are techniques you can do to try to, so this is a imagination of if we brought that end-of-life vehicle scrap in to make a new car. There's plenty of things you can do along this supply chain that you've heard about in the previous talks. So more disassembly, better shredding, better sorting. It is interesting to think about vehicle electrification. Electric vehicles use about 3 times more copper as a conventional. So with that much more copper there, it should be better taken care of. You can technically do a chemical extraction at this point in the steel melt. You can also use different casting techniques to increase the tolerance of your copper. And then you can also design cars differently to perhaps have less copper content or to make all that copper wiring easily detachable. And of course, with the delay between car production and recycling, there will be that delay there. So the area I'm very interested in is this chemical extraction step, because I think it's an area that's been fairly neglected. It is a tough area to be in, but it's a nice behind the scenes solution if you can get it to work. So what I did was I looked and tried to imagine all of the ways you could remove copper from a steel melt. I looked into the mechanisms to try to get it into a different phase and what physical or chemical properties you would exploit to get it to move there. And I also looked at experimental results of those proposed processes. I tried to imagine how it would fit within conventional steel making to try to define a process so that I could then estimate how much energy would be required to remove copper from a very contaminated mix. So that's like 0.4 weight% down to a concentration that would allow you to make a new vehicle about 0.1 weight%. And so the good news is that there are solutions. They are a little bit energy intensive, but it's really just 10 to 20% of the melting energy of an electric arc furnace. So adding that 10 to 20% might be justified in the future. Of course, the devil is in the details, and the cost needs to be very carefully considered, but really kind of looking back at the prior art and trying to innovate around this space might be valuable in the future. And this is just a map of what's known from the literature currently. I came to MIT 3 years ago and have been working in Professor Eleanor's group on this project on decomposing this mineral called chalcopyrite electrolytically with the purpose to make copper. So in this process, we decompose it. Sulfur evolves at the anode, and the two metals here, copper and iron, deposit at the cathode. And what we thought, you would imagine just by looking at standard state thermodynamics, is that copper and iron would deposit as this mess in the cathode. But what we found is actually that the iron deposits first. The iron comes out nearly completely on its own, and it's not until the iron is very much depleted that copper then deposits at the cathode. So there's this kind of unexpected processing space where now we're able to make this iron completely electrolytically without CO2 emissions. And we're going to continue exploring this area to see what the limits of copper control are there too. And then I've also looked into another process that is much simpler, but could work as well. So the copper is present as external contaminants, as wire and little bits in the steel scrap, and it melts at a lower melting point than steel. So you could imagine maybe a situation where you melt the copper first, and if it doesn't stick to the steel scrap, it should fall away. And I found conditions where indeed it forms a stable droplet that could then be wicked away from the steel scrap. You do have to be careful because there are conditions where it very much sticks to the steel scrap. But I think this is also possibly a low-hanging fruit kind of opportunity where we are seeing some scrap preheating systems coming online, where it's a conveyor belt of scrap that's preheated. It saves on energy, it's more productive. And so maybe there would be a chance to also try to remove some melted copper along the way. My point overall is just that we will have to come to grips with this iron copper separation eventually if we want circular metal systems. They intermingle not just in vehicles, but in all appliances and devices. So it is an important separation to think about and to invest in. So my conclusions overall is that the US could lead the way to develop a circular steel system and meet all of our domestic supply with the scrap that we generate. I think vehicles are a great place to start with that, and we need to manage copper, but there are plenty of solutions to explore there. So thank you very much. I'll wrap up so that we can also get lunch.
Thank you for a great talk, Katie. Any questions or comments from the audience? Sort of curious how maybe some of the recycling folks, or maybe Daehn from Nucor, if you're still online, what your reactions are.
Yeah, I thought that the presentation was very good, very interesting, and actually complemented mine quite well. Thank you for that information. By the way, the preheating of scrap is called the Consteel process, which is used at some places. Copper is a little bit more challenging when you're trying to remove it in the high temperature phase, and that's because copper tends to wick toward the and wet the grain boundaries. And so we've found that it's not as simple as just heating it up and then blowing it away. It doesn't work quite like that. The best way and probably the most efficient way that we've, viewed it is get rid of it before it gets into the scrap stream. But otherwise, nice presentation.
Thank you. Just a quick question, Katie, looking at your graph on the bottom right here. I know those are some bubbles, so I don't know how well defined those boundaries are, but I think I saw earlier maybe 0.06% copper limits for sheet. So is it that even if we applied these processes, you're still talking about sort of 50% dilution might be needed to get you down to sheet levels of copper?
That's a really good question. And that's, I think, something that would need to be kind of worked out, perhaps iteratively, industrially. These processes were all done at the lab scale. So some of this rate of removal has been done on kind of simulated scrap or at a very small scale that it's not completely sure what the limits are. Or so I defined that limit of 0.1 as a way to do the analysis. But I think you could possibly go lower, and there is kind of a maybe diminishing returns phenomena that can happen of trying to get that last little bit out. Might be more trouble than it's worth. So it would be kind of a dynamic thing you would have to figure out with, is there pig iron available? Is there DRI? Is it really worth it energetically to do that last bit of separation? But
I don't know if this connects to your current project at MIT, but are there any iron ores which just have a lot of copper in and sort of is there anywhere where on the primary side they've had to deal with this?
The iron ore does not have copper in it. So that's why it's also why there's not really a great solution for it from the iron industry side, because it's not a problem that's been dealt with before recycling, really. But it is, I did find it very interesting to come at it from the copper industry side, where there is iron in the copper ores, and the way that that's dealt with is just to oxidize the iron completely, and it becomes an iron silicate slag that can be used for aggregates or kind of low value things. But we are thinking that it is interesting you can get this metallic iron out of that mineral with our new process.
There's a question which came in through the chat from John Wuritz. I hope I pronounced your name correctly there, from the Aluminum Association. Why is so much copper wiring used in vehicles? Aluminum is more conductive by mass, and presumably wouldn't be a contaminant to the steel if you had aluminum wire either. So do you know?
Yeah.
Have people thought about that?
That is a solution that I've seen before, and me as not a car designer, I don't know exactly why that hasn't taken off, but I've seen some proposals for that, within the last 15 to 20 years. So it is an idea that's been around, and I don't know why not aluminum exactly.
Aluminum wiring is a more of a challenge from a connection standpoint. You're going to have some more corrosion, and in the vehicles, corrosion is a crucial thing. So they're going to have a very difficult time with that. And by the way, as far as copper, rebar is almost entirely shredded scrap. I mean, they don't put anything else in there because they try to make it as cheap as possible, and the copper actually helps because it improves corrosion resistance. But when you're talking about sheet steel, you're talking 0.06. When it gets down to very, very ductile grades, that's when you have to limit the amount of copper, because you can't meet the tensile strength maximums that are required. Otherwise, most of your HSLAs, dual phase, and in conventional steels, it's not a problem. You can add some copper, but depending on the thickness, it may cause hot short, which you have to deal with. But otherwise, it's not a problem.
Thank you. Well, that's great. maybe we should let people get some lunch. I know we're a little bit over time. Thank you again, Katie.
Oh, thank you.
So let's meet back still at the scheduled time of 1:10. So that still gives us 45 minutes or so for lunch. And then we'll really looking forward to this afternoon sessions where we'll hear more from you guys in the breakout sessions. So see you at 1:10.